Welcome everyone for today's quantum spacetime seminar. Today we are delighted to have Professor Nima Arkani-Hamed from Institute for Advanced Studies, Princeton. And today he's going to tell us about particles and strings, polytopes and binary geometries. Spacetime quantum mechanics, particles and strings, polytopes and binary geometries. So over to you, Nima. Yeah.
All right, guys. Well, I'm really delighted to be able to join you, even if virtually. I do hope in the not too asymptotic future to be able to come and visit India again. It's one of my favorite places to visit. So indeed, I'm going to be talking about, well, broadly, a line of work that I've been engaged in for around 12 years now with a wonderful group of roughly equal numbers of physicists and mathematicians. There will be no references interspersed throughout this talk. This is just a big list of people I've been working with. Although some of the work that really has been going on most intensively over the course of the pandemic is with these underlined people, the mathematicians Hugh Thomas and Pierre-Guy Plamondon, and two wonderful young physicists, Giulio Salvatore, who's now a postdoc at the Institute, and Hadley Frost, who's at Oxford. As we all know, the foundations of our understanding of the physical world, quantum field theory, is born of the union of space-time, the principles of space-time and quantum mechanics. And they're also the major storm clouds that I think almost all of us agree on with the first point. Maybe the second point is a little more controversial. But it seems very likely that the notion of space-time is likely an approximate concept, and that some more fundamental description of physics will remove it. And that perhaps even extensions to quantum mechanics will be needed to address the deepest questions about cosmology. I'm not talking about any modification of quantum mechanics in a random Stern-Gerlach experiment in a random lab somewhere. I believe that in every situation where quantum mechanics can give a well-defined answer, it gives the correct answer. But there are situations where what's needed to make well-defined quantum mechanical statements are not obviously available. Which show up in questions like applying quantum mechanics to the entire universe, and perhaps that will call for some extension to quantum mechanics. Now, the arena in which many of these questions have most fruitfully been attacked over the past 20 plus years now is the context of AdvancedStudies, where we have our sort of first gateway drug example of the idea of emergent spacetime, where if we imagine that our universe is, if we imagine a universe which is the ADS tin can, and we ping things on the boundaries of the tin can, the observable, in this case, the boundary observable, the well-defined quantum mechanical observable, when we also have gravity or ADS boundary correlators. And there's, because the observable starts and ends on the boundary, it's reasonable to ask for a theory that lives on the boundary that computes it, and there's an ordinary quantum mechanical theory on the boundary that's albeit strongly coupled, but which produces the results to these observables. Of course, famously in this case, the time that flows on the boundary is the same as the time that flows in the bulk. So this is an example not of emergent space-time, but of emergent space, and gravity and strings and everything else, but time is left alone. Now, one significant closer step to the real world is the case of asymptotically flat space, where the observables are instead, the boundary observables are instead scattering amplitudes. And of course, this is the dual role played by scattering amplitudes. So on the one hand, they're the sort of formal, well-defined asymptotic observable in asymptotically flat space. That's, for example, the reason why string theory to begin with was a theory of the S matrix. On the other hand, they also have a central practical role to play in fundamental physics as being the main observable that we care about in high-energy physics experiments. Not just at things like the LHC, of course, human-engineered experiments, but also things that happen everywhere all the time in the world around us. Sort of elementary particles, particle scattering processes are maybe the most basic process in nature that takes place all the time everywhere. But if we think about making predictions at the LHC, you know, famously, in order to be able to understand the backgrounds well enough to be able to extract new physics signals, you really have to understand the backgrounds from ordinary standard model processes incredibly well. That's because the sort of rates of ordinary collisions, you know, we have like 1 billion collisions a second, maybe we produce 10 top quark pairs every second, but we're looking for things that if we're lucky will take place on the timescales of 1 a minute or 1 an hour. And once it gets to 1 every decade, then we won't even see it. But that's the sort of time scale that we're talking about. And so clearly you have to be able to extract, you have to be able to predict ordinary backgrounds with high precision to be able to subtract them and see the signal. So that's a practical reason for caring about scattering amplitudes for something that goes even beyond the very, very simplest processes. So for instance, to be able to look for supersymmetry at the LHC, you really have to have under control processes like 2 gluons in, 3, 4, 5, 6 gluons out to good accuracy. And of course, in principle, there's nothing wrong with this. We know how to do these calculations. This is not new physics. This is not speculative physics. And everything I'll be talking about today is about completely ordinary standard physics, just trying to conceptualize this ordinary standard physics from a new point of view. But if we recap the usual way of thinking about these particle scattering processes, if we really imagine drawing every way these particles could have scattered as processes in space-time, every process is supposed to reflect the fact that the interactions are local in space-time, and then we're supposed to add up all the different ways the interactions could have taken place in order to satisfy the rules of quantum mechanics via the sort of the Feynman path integral picture for what's going on. And it's clear that if you do this, there's immediately a combinatorial explosion in apparent complexity. This is what the calculation looks like, even for, I think this is 2 to 3 gluons, not even 2 to 4, but you get lots of dense pages of algebra when you go beyond the very, very simplest processes. And yet a little over 30 years ago, people discovered, starting with this remarkable paper of Park and Taylor, that these hundreds of pages of algebra in some cases collapse to shockingly simple expressions, like a single term. And back then it was not universally recognized that this was the tip of a giant iceberg. Today we know it's the tip of a giant iceberg. And that Feynman's way of thinking about this physics, this is really even the standard formalism of quantum field theory, that has a purpose in life of making the usual rules of space-time and quantum mechanics manifest, is doing that correctly, of course, but is clearly also obviously hiding some extraordinary new structures. And we'd like to understand what those new structures are. And in a sense, you know, sometimes this activity in thinking about scattering amplitudes from the on-shell point of view that I'll talk about, sometimes it's characterized as sort of more efficient ways of calculating amplitudes. And that's one aspect of it. But to me, it's a very derivative aspect of a more fundamentally different attitude. We don't care so much, at least I don't care so much, to find what the final formulas are per se. What we're actually after is a different question. We'd like to find a different question to which the amplitudes are the answer. Now, the standard question to which the amplitudes are the answer is, well, you imagine that you have some asymptotic particles, and you want to know what's happening that gives rise to this pattern that we encode in the amplitudes. And the conventional answer is that we fill in the rest of the picture with the interior of the space-time beyond the asymptotics, and the usual picture for what's going on in this interior is local unitary evolution in space-time. And what we'd like to do is find a different question to which the amplitudes are the answer. A different question that does not put in a priori that there is an interior of the space-time, that does not put in a priori there's anything like a Hilbert space or unitary evolution or wave functions or the Schrodinger equation or anything like that. We want to see a different question that's intrinsically posed in the kinematic space that defines the amplitude, that gives the amplitude as the answer, and in so doing, begin to see how this something else gives rise to the properties of amplitudes that we ordinarily ascribe to the existence of both space-time and quantum mechanics. And I think the overriding sort of vision here, may or may not come true, but the overriding vision is that unlike what we've gotten used to with ADS, where sort of quantum mechanics is king and space and gravity and everything else emerges, but time is left alone, that in now talking about these dynamical processes where time plays a crucial role, that there's some other set of ideas, and that we'll see that quantum mechanics and space-time somehow emerge together, joined at the hip from this more abstract, perhaps to begin with, more alien-seeming set of ideas. As I said, that's the sort of vision. It may or may not come true, but what I've been seeing with my friends over the past 12 years is a number of very concrete, not like just slogans, but very concrete, explicit examples of this kind of a picture. And I think even before getting going, it's clear that if there's some deeper structure underlying space-time and quantum mechanics, it must involve new physical and mathematical ideas. And I just want to begin by talking about what the sort of obvious physical idea is. The obvious physical idea is associated with these words on shell versus off shell. So if we think about a particle moving along, the normal way that we would specify its kinematics is by giving its form momentum, let's say, so it has some energy and momentum p. But these are constrained to lie on the mass shell. We have to have that e squared minus b squared equals m squared. On the other hand, when we think about intermediate propagators in Feynman diagrams, of course, they're all off shell. So we are, in our usual way of thinking, while real particles are things that propagate in from infinity or go back out to infinity, they propagate over infinite distance, and that's what puts them exactly on shell. What we're doing when we fill in these pictures with virtual particles that travel over finite distances, what we're doing is they're introducing some fiction that's needed to manifest the usual rules of space-time and quantum mechanics, locality and unitarity. And it's very clear that this is the origin of all the horrible complexity in the intermediate stages of the calculations. That's especially clear when you have gauge theories in gravity, when you're carrying around like large amounts of gauge and diff redundancies as well. But as we'll see, and what we'll talk about today are the dead simplest, dumbest theories of just phi cubed like theories, where there isn't even any excuse that there's some gauge redundancy around. And even here, we're going to see that there is hidden simplicity, hidden symmetries that are brought to light by these other structures. So in any case, the physical idea here is to eliminate virtual particles and try as much as possible to describe this physics on shell. Now, how can we do this? After all, there is a point in having all those virtual particles, is they're making locality and unitarity as manifest as possible. So how can we see that there is locality and unitarity if we're not going to have the usual apparatus of the virtual particles in the inside of the diagrams? And what I'll describe here, and mostly for this talk, I'll talk about things at tree level, although I'll indicate, as I said, most of what we've been doing over the course of the pandemic is figuring out how these things extend to all loop orders and beyond the planar limit and so on. So I will say a little bit about what those things are, but just to make the ideas as clear as possible, let me focus on the simplest case at tree level. So imagine that, yes, was there a question?
Sorry, just clearing my throat. Sorry.
Oh, no problem. All right. So imagine that we're exchanging a particle here that have as mass m, and of course, a crucial point is that we can have a resonance when p1 plus p2 squared goes to m squared, and so the amplitude develops a pole in that neighborhood, and so the fact that we have a pole when p1 plus p2 squared goes to m squared. Of course, we interpret as when the virtual particle becomes real. So we know where the poles are. The poles are when a sum of the subset of the momenta go on shell. And then quantum mechanics tells us that on the residue of that pole, we have to be able to interpret the amplitude in the neighborhood of when p1 plus p2 squared equals m squared as simply producing the intermediate particle and having it propagate a long distance and having it decay on the other side. Okay, so locality tells us where the poles are. That the poles are when some subset of momenta go on shell, and unitarity tells us that on that pole we get factorization. That we should think of the residue as the product of lower point amplitudes. So if I summarize, the rules of locality and unitarity are actually sharply reflected in the amplitude at tree level. Locality is that the only poles are when a sum of the subset of momenta go on shell, and unitarity tells us that on that locus where you go on shell, the amplitude should factorize into the product of simpler pieces. Okay, and so that now gives us a concrete strategy for this otherwise very vague-seeming question of find a different question to which the amplitude is the answer. This has now turned into something very concrete. We would like to find some kind of new question that's directly formulated in kinematical space. In other words, in the space that labels the scattering process, to which the amplitude is the answer without ever talking about the interior of space-time or a Hilbert space. Okay, and which nonetheless, in particular, gives correct poles and the correct location of the poles and the correct pattern of factorization.
So, sorry, Nima, can I ask you something here?
Sure. Yeah.
Sorry, I know the subject very poorly, but is there something more to be said in terms of branch cuts and so on, or is it do the poles encode all the locality and so on aspects?
Yeah. So right here, I've just been talking about tree level, so there are no branch cuts. But indeed, the really hard part of the subject is to know exactly what the singularity structure should look like at loop level. Okay, so and in a sense, that was the sort of S matrix program of the 1960s, was to attempt to derive somehow from the top down what the singularity, what the analytic structure of the S matrix should be, what the branch cut structure should be to reflect causality. The really hard part is causality. Checking unitarity is easy. Checking Lorentz invariance is trivial if you just work with Mandelstam invariance and so on. However, what's non-trivial is if I hand you a function and say this is an amplitude, it's non-trivial to check whether somehow it could have been arrived at as the answer to a causal question. After all, you're just given this information at infinity, and you want to figure out what property of the answer encodes that it came from something causal. And to this day, we don't know the answer to this question. This is where the S matrix people failed. They really couldn't find the ab initio answer to this question. They even attempted to cheat by looking at field theory to try to guess what the answer to the question was, and they still couldn't really find the answer to this question. In some cases, we can do better. For example, we do know the answer at one loop, not just at tree level. We know the answer at one loop. Beyond that, if you have a notion of the sort of loop integrand, the thing that if you integrate over loop momentum, you get the amplitude, then at the level of the loop integrand, it's again relatively simple. That locality says that it should look like it's built out of sort of propagators of local diagrams, and unitarity says that that cuts of these integrands should sort of factorize into lower point processes. So sometimes we can have crutches. When we have the integrand, we know what it means because ultimately we're dealing with rational functions. But we don't yet know what the answer is supposed to be in complete generality. And this is the sort of big difference between this subject and, let me contrast it with the conformal bootstrap. Okay, there it's just a completely well-defined hard math problem. That if someone claims that they've figured out what some consistent 4-point functions are for some CFT, you can check whether they're lying. You can check whether they're right or wrong. You check whether it has the correct operator product expansion, and that's it. And ultimately, it's because those questions are about Euclidean quantum field theory. We know everything about Euclidean quantum field theory. At least we know what the rules are, and so we know how to check whether you're right or wrong. Here, and that's the sense in which going to amplitudes is one sort of significant step closer to the deeper questions about time. Here, it's a question where time is hardwired into the nature of the observable to begin with. There is no useful Euclidean continuation of the amplitudes, and so we just don't know a priori. We don't know what the answer is for what functions the amplitudes are made of. There's no analog of conformal blocks or the kind of standard expansions that we're used to in CFTs. And so I think it's kind of shocking that into the third decade of the 21st century, we don't know the answer to such incredibly basic physical questions about the real world. But anyway, there we are. So in this talk,
I have a question in continuation of this, Nima. Since you're saying generality still, it seems that I mean, if you're looking at a quantum field theory which is not gravitational, there's a stronger sense of locality in that you want microcausality to be obeyed. But since you're talking about theories where maybe time emerges and space emerges, maybe theories of gravity, then the only locality we expect is just asymptotic locality, right? And that is not so hard to formulate if you don't care about what's happening in the bulk and you just want to maintain asymptotic locality. I mean, isn't it an easier problem?
No, I think even I mean, we know some aspects of it. Like we know that the 2 to 2 amplitudes have to be they have to be well behaved in the Regge limit and so on. They have to be polynomially bounded in the Regge limit and so on. But I mean, really, the practical question, and it doesn't have to do with whether it's gravitational or not, is if I just hand you an amplitude, how do you know if it's right or wrong? We don't know how to check if it's right or wrong. We can check that it's wrong, but we don't know how to check in all details that it's right. Yeah.
Sorry, Nima, one question.
Yes.
So when one says loop integrand or loop integration, isn't one falling, back on the picture of Feynman diagrams and virtual particles?
No, not necessarily.
Loop answer directly from this abstract object.
Right. So not necessarily any more than you are at tree level. So it's true that it's still slightly intermediate in that you do have these L's lying around, but nothing on the face of it tells you that the L's have to be grouped together in something that looks like diagrams that you're adding together in some way. There are just some extra labels, and we'll be still looking for sort of rational functions in those extra labels that have poles in particular spots and that factorize appropriately on those poles or cut appropriately on those poles. So yeah.
But can one expect a nice enough structure already in the full answer, or?
Yes, we can. It's just that's at the moment that's a harder problem. But if I was giving you a different talk, I would be talking about that. I mean, what kind of non-perturbative questions that you might ask in kinematic space are that might actually give you the amplitude. That's also a very interesting. That's also a very interesting question, obviously. And that question and the question I'm asking here today are very closely related to each other. Anyway, since my goal today is just to kind of give you a flavor of the kind of objects and ideas that show up in this business, mostly just in order to have concrete things to look at. I'll be talking about things at tree level, although, as I said, I will nod as we go along to what we've been learning over the past year and a half on the extensions to all loop order and beyond the planar limit. Okay.
Now, also one more question. When you compared conform field theories and said that CFTs, we have this conform block expansion, operator product expansion, and so on. So why wouldn't one think of the partial wave expansion in the same way? I mean,
because writing down a partial wave expansion does not remotely guarantee that you have a well-defined amplitude. So it's something that has to be satisfied, but it's not remotely enough to guarantee that it's okay. So what you need is something which has some appropriate analytic properties in both S and T, for example, at 4 points. When you do a partial wave expansion, you're choosing a channel. You're choosing the S channel, and then you can write something that's unitary and so on, and as a function of cos theta. But it's not at all obvious that the resulting object is something which is appropriately well behaved as a function of both S and T.
Okay, thank you.
In a sense, it's the fact that in conformal field, I mean, it's really the sort of wonder. It's an extra thing in CFTs that sort of inversions allow you to see everything in one channel. Okay, that's kind of that's the extra wonderful thing about CFPs, in addition to the Euclidean nature. But the perfect analog of that is that you begin you begin by writing a partial wave expansion of the S channel. It just does not tell you enough about what's going on in the other channels to be able to guarantee that you get something unitary. All right, so our concrete strategy, I think I just said it, is we do want to find this different question, which gives us a function that has poles in the same poles where it's supposed to, and factorizes correctly. And the picture that's been emerging over the past decade is that our kinematic space, what could the kinematic space be? It's really any way of sort of labeling the on-shell scattering process. The analog and the analog for boundary correlator, what is the kinematic space in ADS? It's just the space of points on the boundary. So it's just the one lower dimensional boundary, which is a perfectly ordinary flat space with a notion of distance, a notion of time, locality. So once, of course, we take the huge step to be in the holographic mindset, it's perfectly reasonable that we should ask for some kind of quantum mechanical theory that lives on the boundary. Here, the analog for amplitudes, in any way of thinking about it, is more unfamiliar. Perhaps the most geometric way of thinking about it are points on the celestial sphere, or twistor space, where light rays go, the space of light rays in space-time, or just the space of n on-shell momenta. Let's say the particles are massless, n null momenta, or the Mandelstam invariance. These are all different ways of just labeling the scattering process. And in these seemingly very arid, boring, dry spaces, like the space of n null momenta, what the hell are you supposed to do in the space of n null momenta? Well, that's what we've been finding over the past decade or so, is that in these seemingly very dry spaces, there's a frisson of combinatorics that then brings to life certain geometric structures that are then associated with some analytic structures. So in kinematic space, there are some shapes, and the amplitudes are forms that have prescribed sort of singularities on the boundaries of these shapes. Okay? The words that go along with these ideas are associahedra, which is where these things were originally seen in n=4 super Yang mills. And then starting around 4 years ago, much simpler versions of these ideas in the context of just simple scalar field theories, associahedra, avatars of these things at a very baby level beginning to be seen in cosmology. And just broadly, what I find exciting about the subject is that it describes the physics of the real world that we see when we look outside the window in a reasonable approximation. It exposes hidden symmetries and new mathematical structures and a lot of pure magic in physics that's right under our noses. All right, so I have learned the hard way in giving talks about this subject that even by my sad standards of keeping time in seminars, it is difficult to talk about everything in a completely to talk about all aspects of the subject in a reasonable sort of 1.5 hour talk. So what I'm going to do today is give you a number of self-contained vignettes. Okay, so that the idea is that you could even fall asleep for any one of these three things, but if you woke up, you would have something totally concrete that you could even go and play with on your own if you were curious and you wanted to play with it. Okay. This has the disadvantage that it's not clear how they all fit into some large coherent structure. You'll just have to believe me that there is a sort of larger coherent structure of ideas that these things all fit into. But I think this is the way to go to for things to be maximally interesting, I hope.
Nima,
so I want to begin.
Sorry,
yes.
I just want you to know that we believe in the old world notion of time. So you don't constrained by 1.5 or even
right,
2 hours.
Good. Very good. All right. All right. So I want to begin with an invitation of how, a very simple-minded experimentalist could discover the hidden combinatorial geometry that I'm going to be telling you about. And then I'll tell you about positivity, polytopes, and how they're related to particles. And then that there's a closely related, like really closely related, but even more rigid kind of geometry associated with this combinatorics that we call binary geometries that give us a curvy version of these polytopes. And that and the physical interpretation of this, if the positivity and the polytopes are associated with particles, then the binary version of these polytopes, as we'll see, are associated with generalizing particle to string scattering amplitudes. Now, as I said, these are going to be vignettes, and I'm not going to tell you the larger overarching story, but just to flag some of the words. The conceptual framework is associated with a number of new mathematical structures in a variety of areas, in combinatorics, algebra, and geometry. Some of the key words are total positivity, extensions of things like cluster algebras and cluster varieties, tropical geometry and hyperbolic geometry, and perhaps most fundamentally and most shockingly to me, category theory. That the most fundamental ideas involve the notions of representations of quivers and categories of quiver representations. I never thought in my life that I would ever think there was anything useful or interesting about the categories, and I've been proven completely wrong. That there's some totally beefy, real contentful things that this way of thinking about is actually really useful and interesting for. But I won't be I won't be talking about any of these things in detail. Just to sort of flag that those are some of the ideas that are going around in the background. All right, so let's start with this first invitation, and we're going to talk about the simplest theory of scalars. Now, you can imagine here that what we have is an underlying trace phi cube theory. Okay, so phi is an n by n matrix, and the interaction is trace phi cubed. So I'm going to do the usual color ordering of the amplitude, but I'm not going to draw double lines here. So we're just going to draw Feynman diagrams where the external particles are ordered. Okay, they're ordered going around. They're ordered going around clockwise here, for example, 1, 2, 3, 4. In these pictures. All right, so for instance, at tree level, we would have these two diagrams for this ordering 1, 2, 3, 4. We don't have the U channel because it's not planar, right? And here are the two kind of shapes of diagrams that you would have at 6 points. Okay. All right, now something that we see is let's look at what the sort of poles in these diagrams are. So in the 4-point case, I have a pole at P1 plus P2 squared goes to 0, or a pole at P2 plus P3 squared goes to 0. At 6 points in this example, it's P1 plus P2 squared is that line, and this line would be P1 plus P2 plus P3 squared, or of course, P4 plus P5 plus P6 squared with a minus sign, okay, negative P4 plus P5 plus P6 squared. So, all right, so the kinds of variables that we see as poles are sums of consecutive momenta, pi plus 1 dot plus pj minus 1 squared minus m squared. And a very convenient way of thinking about what all these poles are is to just imagine drawing the momenta end to end on a piece of paper. Momentum conservation tells us that the momenta all add up to 0. So we get a closed polygon. And then it's very natural to look at the distance squared between 2 points, I and j, on this polygon. So here's like 1 and 4. The distance squared here that I'll label x14 is P1 plus P2 plus P3 squared, or P4 plus P5 plus P6 squared. Okay. So, so the propagators in these pictures are associated with chords in this polygon. Okay, and it's a very simple thing to check, that the number of these chords, if you have n points, is n times n minus 3 over 2, which is exactly equal to the number of independent Mandelstam invariants. So, so these guys are not only the propagators, they're also a basis for all the Mandelstam invariants that you could have anyway. Okay, so these are the variables that we're going to be using. All right. So now imagine that that's the theory of the world, and there's an experimentalist sort of living at infinity. And they have their finger on the Mandelstam dial, and they twiddle the dials to see what the pattern is about this, what the interesting patterns are about this process. So what do you think the first thing that they would notice is? Probably the first thing they would notice is that there are some, for some choices of the Mandelstam invariants, they can make the amplitude blow up. Okay, so they would notice that the amplitude has poles. And what they do with this information depends on the kind of experimentalist they are. Anyone who knows experimental particle physicists know there's two kinds: those who secretly want it to be theorists, and those who just hate theorists. Okay, so let's first talk about the one who secretly wants to be a theorist. They know there's a pole, so something about residues of poles is very important. So they do lots of detailed measurements of the amplitude in the neighborhood of where it blows up, and they discover something amazing, that the residue factorizes into the product of two lower point amplitudes. So that's the information that they go and they announce at a conference, and there's some theorists in the audience, and depending on their predilections and background, they react to it in a different way. So, for example, if Feynman is sitting in there in the audience, he says, "Oh, I have a theory for what's going on. We have the sum over Feynman diagrams that I'm just naming after me, and there are all these sort of virtual particles in the middle, and I'm summing over all these pictures. But it's obvious that that these will have poles in the correct place, and they'll factorize in the way that the experimentalist has seen." Okay, so that's one reaction to this picture of factorization, is that we have a picture of particles in space-time. There's another theorist in the audience, who's a mathematician, Deline and Mumford, who say, no, I've seen this before too. I don't know what you're talking about, Feynman. I've seen this before. This is what happens, this sort of picture that there's some kind of singular locus where the object splits into the product of lower objects of the same type. This is what happens in the very simplest moduli space you run into. If you just have endpoints on P1, endpoints on the boundary of a disk, then this space also has the property that as the points collide, the moduli space bubbles and factorizes into the product of two simpler moduli spaces in exactly the same way. So in other words, these two facts of the picture of diagrams or the picture of factorizing moduli spaces, the second picture is exactly the picture of the string worldsheet. Okay? So what I'm trying to say here is that if factorization is the star of the show, it is associated with the two sort of standard ways we've had of thinking about particle scattering for the past 50, 60 years. Okay? But there's another experimentalist who's going to be the hero of my story here, who is lazier but smarter. And this person gets excited by the fact that the amplitude is blowing up. So given that they can make it blow up, they don't want to do any detailed measurements. Something exciting has happened, it's blown up. They want to see if they can make it blow up more. Okay, so they can notice that, for example, the amplitude at 4 points only blows up when P1 plus P2 squared goes to M squared. But once they do that, try as they might, they can't make it blow up anymore. Or when P2 plus P3 squared goes to M squared, but again, try as they might, they can't make it happen anymore. So that's the pattern they noticed at 4 points. At 5 points, they notice something a little more interesting, that it can blow up when P1 plus P2 squared goes to M squared. But then once that happens, they can further make it blow up one more time if also P1 plus P2 plus P3 squared goes to M squared. Okay, so that's a pattern that is allowed, but not, let's say, when P1 plus P2 squared goes to M squared and P2 plus P3 plus P4 squared goes to M squared. There's no singularity there. Okay, so there's an interesting pattern in how the poles come together. So let's say this in the language of those of the variables that we talked about. Okay, so P1 plus P2 squared would correspond to this chord. P2 plus P3 squared would correspond to the blue chord. And so we see that we can indeed have a pole corresponding to the purple chord and one corresponding to the blue chord, but not both. Now, if we go to 5 points, then we can have a pole when P1 plus P2 squared goes to 0. And when P1 plus P2 plus P3 squared goes to 0, those are the blue and the purple chords, but not for chords that are crossing each other. Okay. And so indeed, these are the rules of locality and of unitarity in the language of the allowed kinds of poles that you can have in the behavior of the amplitude on those poles. So locality tells us that the pattern of poles that we're allowed to have are chords that don't cross. So you can have 1, 2, 3, however many that you can have, so long as they don't cross. And the maximal set of poles that you could have correspond to what would look like a triangulation of the polygon. Okay. What does unitarity say? Unitarity says that if you put one of these xij's to 0, that on the residue of the pole 1/xij, the amplitude factorizes into the product of what you get as if you just cut the polygon along that line. Okay, so this amplitude times that amplitude with some new external line that is added there in the middle. All right, so if we go back to our experimental.
Can I ask a question? Yeah, in the previous slide,
Yes.
yeah, I understand the bottom half, which is unitarity. Why is the top half
Yes.
related to locality?
Well, the top half is related to locality because one way of saying why this is not allowed is that there's simply no diagram that has all of these poles. There's no local diagram that has all these poles at the same time. It's the same reason why we couldn't have S and T together. There's no way to draw a picture that would have both S and T poles at the same time.
So it's a field theory intuition.
I mean, this whole game is to take some kind of natural fact about is to interpret facts about the amplitude and try to see them as coming from somewhere else. So absolutely, that if we had poles with these crossing chords, then we couldn't possibly draw anything that looked like a local picture to correspond to.
Thank you.
But we're now, but we're now going to see these things come out of a different kind of question. Okay.
So Nima, some of this is tied to the fact that you're looking at color ordered amplitudes, and some of it is
here it's tied to a color ordering. As I said, I will say, and we're talking about we're talking about color theories, but not necessarily the planar limit. Okay, so here we're just talking about tree level, so it's planar. The general story has nothing to do with planarity. So it's really about arbitrary orders in the 1/n expansion, arbitrary genus surfaces. So there's going to be a story for arbitrary genus surfaces.
Okay.
Nima, at least at this stage, these diagrams are duals of Feynman diagrams, right?
Yes, these are exactly. These are just duals of Feynman diagrams. Precisely. Exactly. Yeah.
So, sorry for this remedial question. Color ordering means you just you have some SUN color group and you draw planar diagrams. Is it?
Exactly that. Okay. Yes.
Thank you.
Yeah, but Sandeep, the amplitudes we're looking at here are color ordered. I mean, it's I think a scalar theory, but this is a color ordered amplitude.
Okay. Thanks for that comment.
Yeah, I just didn't draw the double line notation, but I could have drawn it all in double line notation, and that would make it explicitly. All right. Now, if we go back to this experimentalist, they want to, if they want to sort of present their data, the pattern they found, they would find something interesting, that the pattern of how the poles can come together can actually be captured by a shape. And let me begin with the case of n=5 scattering. So here's the idea. Remember, we can have single poles, and then we can have double poles, and they correspond to a single chord or two non-crossing chords. So the idea is that here's a single chord, okay, which is represented as an edge of this pentagon. It's completely coincidental that it's also that it's 5 points and it's a pentagon. We'll see a more interesting example in a second. Okay, but so this edge is associated with the ability to have a single pole, and this other edge is associated with an ability to have a different single pole, but they meet at this vertex, and this vertex is the two poles that can come together consistently. Okay, and so it's slightly interesting that you can represent the pattern of single and double poles that can come together as the facets of some geometric shape. Okay. The interior you can think of as being no poles at all. The codimension 1 boundary is 1 poles. The codimension 2 boundaries are 2 sets of compatible poles, and so on. Okay, so that's what it looks like. This pentagon is what it looks like at 5 points. And if I go back to 4 points, it's a little even more trivial. It looks like an interval. Okay, where the interior is just the sort of square, and on one end I have the, let's say, the S channel, and the other end I have the T channel. All right. Well, it turns out that this is true in general. So this is what the picture looks like for 6 points, and I haven't drawn everything in here. The picture would get a little busy, but this is a famous shape. It's known as the associahedron or the Stashev polytope. It was discovered by mathematicians in the 1960s. And again, what's going on in this picture is it's a three-dimensional shape. And you can see that it has flat faces, so you can even cut it out with flat inequalities. It's a polytope. Something that you can cut out with flat inequalities is, or that you can think of as a convex hull of a bunch of vertices is known as a polytope. So this is a three-dimensional polytope, but such that the facets of this polytope are associated with partial triangulations of a polygon, and that facets meet if the partial triangulations are commonly refined to a more refined triangulation. Okay, so the vertices are actually complete triangulations of the hexagon in this case. But you see, for example, this edge would correspond to having these two poles. This face would correspond to having that one chord. This face would correspond to having that other chord. And you can have fun filling out the whole rest of the picture. And it's remarkable that all of this, the combinatorics of how you can triangulate a polygon are actually polytopal in this way. All right, so this is a fact. It's a qualitative fact about how the poles of the amplitude come together. It's a qualitative fact that is not known to either Feynman or Deleuze. Okay, it's not known. Neither the particle or the string picture makes this fact obvious. However, it's true, and not only is it true, but this shape actually also knows about factorization. Okay? So that's quite remarkable. How does it know about factorization? Well, notice if you look at this picture, it has 6 faces that are pentagons. You see 2 of them here, 2 of them there, the one at the bottom and the one at the back. And it has 3 faces that are squares that I just indicated. Okay, so those are what the faces look like. And in fact, each one of those faces is interpreted as the direct product of the simpler objects of the same type. So this pentagon here, you can really think of as being associated with the factorization or with the factorization of 5-point on one side and 3-point on the other. The 3-point polytope is just a point, so we just get a pentagon from that. Whereas the square faces you can associate with the direct product of a 4-point and a 4-point amplitude, that at the level of the polytope, remember the 4-point amplitude was associated with an interval. So I have an interval and another interval. The product of 2 intervals is a square. Okay, so the pattern of poles is polytopal, and that polytope has a remarkable property that on its faces, it factorizes as a Cartesian product of lower polytopes of the same type. So here again, I've drawn this picture of the associahedron, this time labeled literally with Feynman diagrams just for fun. And again, saying it again, the particle and the string picture don't make this obvious. They don't make it obvious that the pattern of poles is polytopal, but this does know what the particles and strings knows. It does know that that we have factorization because the associahedron factorizes on its facets. The facets of the associahedron are direct products of the 2 lower associahedrons.
Sorry, Nima, I'm sorry to slow you down, but just so I understand, so here this associahedron represents then, as you said, the 6-point amplitude, just to make sure. And
that's right.
Each facet is a chord, if I understand. Is that right?
So you should really think of it as each facet, like each face, literally codimension 1 face is the first factorization channel, and then each edge is a further factorization, and the vertex is the complete factorization into the product of 3-point vertices. Okay. But what would happen is that this guy is associated with one intermediate guy going on shell. This guy is associated with a different intermediate guy going on shell. That edge is associated with both of them going on shell.
Okay. Got it.
And you see, it's not at all obvious that this thing should have this polytopic property. Just to give you just a trivial check, you see, you can certainly count how many complete triangulations are there, or that's how many Feynman diagrams are there, and also how many partial triangulations are there. That's a sort of simple combinatorial count that you could do for any n. But if these things are going to fit into a polytope like this, the Euler sum of all those numbers has to add up to 0. And it's not at all obvious. I mean, you can count them, and there's some interesting hypergeometric identity that makes it true. But it's not obvious. It's not obvious that these things are polytopal directly. Okay, so.
One last really remedial question. I'm really sorry. What is a polytope? I mean.
Oh yeah, sorry. I said that quickly. A polytope is anything that you can cut out with linear equations. Okay, so if you just imagine in the plane, you say x is bigger than 0, x is bigger than 0, y is bigger than 0, 1 minus x minus y is bigger than 0. That would cut out the interior of a triangle. If you put extra linear equalities, it would cut out the interior of some polygon. Okay. Well, in general, in an n-dimensional space, anything that you can cut out by a bunch of linear inequalities is called a polytope. Okay. More precisely, that's called the facet description of a polytope. Okay. Another description is if you give a bunch of vertices, and then you say, look at all the weighted sums of those vertices. That's called the convex hull. So if you look at all the weighted sums of the vertices, that also gives you a polytope. Okay. So those are two complementary, literally dual descriptions of a polytope. Okay. Did that answer your question, Sandeep?
Yes. Thank you. Sorry for these.
No, not at all. Not at all. Please continue to stop me with any questions like this.
Sorry, so weighted sum means plus or minus 1?
No. The weighted sum means that they're weighted with positive numbers such that the sum is equal to 1.
Yeah. Exactly.
Okay. Thank you.
Nima, I mean, this picture we thought of as a picture of modular space of string, right?
That's right. I will come to that in a moment. Exactly. Except here we've said nothing about strings, nothing about any of that. Right. So that's a sort of part 0 of this subject in some sense, is that it's possible to see stringy things without strings, with no alpha prime anywhere. And in fact, So just hang on for a little bit. Yeah.
And from what you have said so far, I mean, the flatness is not yet clear, right? I mean, this is just a topology. So far, you just
That's right. So far, this is a topology. Well, I mean, it's clear simply because I've drawn it so that it looks flat. But in fact, since you asked, when Jim Stashev discovered these things, he did not actually, he knew it topologically, but he did not know how to cut them out with inequalities. And the story is that his PhD advisor actually brought a cardboard cutout of this shape to his PhD thesis defense to at least make it clear that it was possible to do it in the case of 6 points. And it wasn't until the early 1980s where people understood systematically how to cut them out as polytopes. And the kind of interest in this kind of subject has been gone up a lot in the last, purely in mathematics in the last 10, 15 years, when generalizations of objects like this showed up in cluster algebras. And anyway, and in a sense, what we're doing is giving a different point of view and generalizations in a number of directions of some of these ideas, especially in ways that are especially connected to the physics of amplitudes. Okay, but in just a moment, we're going to sort of explain where this comes from. Here I've just drawn it. I'm going to sort of explain conceptually where it comes from. All right. Now, actually, my friends and I sort of got into the subject around 4 years ago by essentially accidentally running into a very particular realization of the associahedron. Okay, so this is our realization of the associahedron. The mathematicians now call it the ABHY associahedron. And you'll notice that it's kind of the same as the one that we are talking about. I mean, it's the same shape, it's the same combinatorics. It still has 6 pentagonal faces, 3 square faces. They meet in the same ways. But it's a very particular realization. It has all sorts of parallel sides and other interesting features if you look at it more carefully. So again, we'd like to know, how do we make this obvious? So we sort of guessed it, but we want a more systematic picture of where these things come from. All right, so, okay, so that's, yes.
So please excuse me, can I ask you the following dumb question? If I just take various pieces of cardboard which can be put together, say to enclose something, would I get a acceptable polytope, and would it describe some diagram in field theory and string theory?
Yeah, no, sure. Anything that you cut out with flat faces and put together, anything that you cut out with like linear inequalities is a polytope. Definitely not a random polytope will be associated with the field theory. And in fact, that's part of now what we're going to talk about. So this was the invitation. The invitation, what you're supposed to get from this invitation is that there's a fact even about stupid tree amplitudes for this dumb scalar theory that is not in our textbooks. Okay, what is in our textbooks is this. What is in our textbooks is factorization. Okay, we know factorization is important. And factorization is made manifest by the picture of Feynman diagrams and the picture of the string world sheet. Okay, so these are and so the most important standard ways of thinking about scattering amplitudes are all about factorization. But there's more. There's more. There's this sort of fact, that simpler combinatorial fact, that the pattern of poles, the way they come together, is captured by a polytope. And that polytope is a very special property. Not only is it a polytope, but it's a special property that when you go to its boundaries, what the boundary looks like is the product of two lower polytopes. That fact that the boundaries look at the product of two lower things is what factorization is, okay? And that would definitely not be true of completely random polytopes. Will not have that kind of property, okay? So what we're gonna be trying to make manifest now in this second part of the talk is where these things really come from, or what kind of set of ideas make the existence of these things obvious. In other words, why I now want to make obvious that there is a polytope that has a property that it factorizes on its boundaries into simpler polytopes of exactly the same in the same class. Okay.
Thank you.
Did that at least partially answer your question?
Yeah. Thank you.
All right. Okay. So so we're now going to talk about positivity, polytopes, and particles. And what I want to do is, so let's go all the way back and think about what our kinematic space is, okay? Our kinematic space in this problem is just the space of all these variables xi, j, right? And so the first thing I'm going to do is just draw them, okay? I'm just going to represent the xij graphically on a piece of paper, okay? So remember, the xij are the chords of this polygon. So the adjacent guys would just be like xii plus 1 would just be the momentum squared for pi. Okay, so that's some fixed number. That's the mass squared of the particle. Or maybe we'll just say that they're massless, just so I don't have to keep saying m squared. Although so imagine the particles are massless, although they can have any mass you like. Okay, so so the edges here of the polygon, they're all equal. The x's are equal to 0. So I'm denoting them in this picture with black. So this would be x12 is 0. But then I'm going to just draw the rest of the indices, because there's naturally a cyclic ordering. I'm going to draw the rest of the indices as 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then this is a 7-point problem, the picture I've drawn here. So I end with 1, 7 up there. And then in the obvious way, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 1, and so on. Okay? I've tilted it in this way just for convenience. Okay? I could have drawn it any way I like. I've tilted it to look like the strip for convenience. All right, so this is just a picture. This is just capturing what all of the variables are, all the xij's are. Okay, so this is our kinematic space. And again, so this is supposed to sort of highlight our challenge. This is not like a boundary at ADS where we go and we find some normal place with a metric and time and blah, blah, blah. This is our kinematic space, just this stupid strip, right? So what are we going to do in this stupid strip of xij's? Well, we're going to find some interesting questions to ask in this space, whose answer is going to end up bringing to life the associahedron and everything else that I was telling you about before. All right. But to begin with, I'm going to justify this word that it's actually a kinematic space-time. So, in other words, in this kinematic space, in the way I've drawn it, there's actually, it's useful to think about a notion of space and time. So the notion of time is going to be going up the strip. The notion of strip is, the notion of space is horizontal. Actually, notice it won't matter that much, but there's actually, there's a Mobius identification on the strip. Because remember, xij and xji correspond to the same chord. So here is 1, 3 down here, and there's 3, 1 up there. Okay, so in general, if I had a point sort of xt, which is ij, then this point sort of 1 minus x, 1 plus t up there would be ji. So there's this interesting Mobius identification on this strip. But now comes the real point, why the word space-time is kind of interesting here, at least as something evocative. We know that it's going to end up mattering in our story whether ij and kl, whether two chords cross or not. So it's very simple to translate what two chords crossing means in this picture of this kinematic spacetime. If you have ij and kl and they correspond to chords that cross, then that means that ij and kl are the past and future corners of a causal diamond that fits inside this strip. Okay, so that's very easy to see. Okay, so compatibility, in other words, whether chords cross or not, they cross if ij and kl are the past and future corners of a causal diamond that fits inside this space-time. All right, let's go back to the picture, and clearly we want to talk about all the variables non-redundantly. I want to talk about xij, but not xji. I want to keep all the variables once and only once. And so I'm going to take a strip out of this picture, which covers all the variables once and only once. And there's many ways of doing it, but I'm gonna choose for the rest of this part of the talk this very simple one. So you can see that every variable in this sort of in this right triangle is covered once and only once. There's 1, 3 is over here, but 3, 1 is not in the green region. It is out there. All right. So let's draw our example here again. I've switched colors. I'm sorry. So now the guys that are 0, which are over here, and at this edge, I've drawn in red, and here are all the rest of the variables. And now is where we're going to put quote unquote dynamics into this space. The notion of positivity is going to make 2 important appearances here. So this is our kinematic space, and now we're going to ask a question in this kinematic space. We're going to ask that all of these variables are positive. All these xij's are positive. The guys at the boundaries are 0, okay, but the rest are all positive. And we're going to put in something that looks like dynamics in this kinematic space-time. We're going to impose that for any mesh in this picture, it has a past and a future and a left and a right. We're going to impose the equation x past plus x future minus x left minus x right equals a constant. With every mesh, there'll be a corresponding mesh constant. And you can really think of this as a discretized lattice wave equation, okay, in this kinematic space-time. As you can see, if you imagine making this mesh smaller and smaller, this difference exactly turns into the discrete double derivative like du dv. C would just be some current. So this is a lattice version of the wave equation. Now, since this is a vignette, I can't tell you why it's inevitable that you have to write something like this down and how it connects to the rest of the structure that tells you that you should do this. But I hope that this is enough to see there's a very simple thing that you can do in this space. You have positivity of the x's, positivity of these sources for this discrete lattice wave equation. All right.
Sorry, Nima, can I ask you something here? So the xi I plus 1 is 0 for all the red dots, as I
That's
gather.
right. That's right.
But now 2, 7 in a sense is also on the null boundary, but there it's not
But it's
0.
not 0. That's right. It's not 0. Exactly. Everything else is not 0. Everything else is not 0. And in fact, it's very easy to see that if you just specify the values, let's say on this pass boundary, if you specify x13, 14, 15, 16 just on the pass boundary, all the other x's inside are specified. Okay, so that's what I'm actually going to show you how it explicitly works, starting in simpler cases. So this is what it would look like for the case of n equals 4. Okay, so this is our picture. And so what are our equations? Well, here we just have one mesh. So the equations are x13 plus x24 minus x23 minus x14 is equal to this mesh constant c. X23 and x14 both happen to be 0. So this is extremely simple equation. X13 plus x24 equals c, but we want both x13 to be positive and x24 to be positive. But now I can solve for x24 in terms of x13. So x24 is c minus x13. And now, so if I demand that x13 is positive and x24 is positive, and I plot what things look like, let's say in x13 space, then I see in x13 space, x13 is positive, but it's also less than c. So in x13 space, I get the inside of this little interval. Okay, so that's the case of 4-point scattering, the 4-point problem. Now let's go to the 5-point problem. Here's sort of 1, 3, 1, 4. I draw the meshes again, and I have these 3 relations now. Okay, so I have x13 plus x24 minus x23 minus x14 is c. That's that constant. Similarly, the equation for this guy and the equation for that guy. All right, and so I have now 3 equations that I can use to solve for x24, x25, and x35 in terms of my x13 and x14. Mm-hmm. All right, and if we solve them, this is the picture that we get. X13 has got to be positive, x14 has got to be positive. Okay? So we have to live in this upper quadrant, but I get 3 more inequalities from x24 being positive, x25 being positive, and x35 being positive. And the picture ends up being exactly this nice pentagon. Okay, and if you keep going at 6 points, if you fill it all out, exactly the same thing. Now I have, you see, now I have 6 points here: 2, 4, 2, 5, 2, 6, 3, 5, 3, 6, 4, 6. There are 6 points. I have 6 equations from these meshes, so I can use those 6 equations to solve for these 6 points in terms of 1, 3, 1, 4, and 1, 5. And so I'm living in the upper octant for 1, 3, 1, 4, and 1, 5, but I'm getting 6 more inequalities coming from these 6 points being positive. And when you work it out, you get exactly this shape of that ABHY associahedron that I was telling you about before, that we had sort of guessed from other motivations. Okay, so why is this happening? So and the claim is that in general, if you do this at endpoints, just this question, the positive solution of the wave equation with positive source inside this diamond, what it gives you is exactly the associahedron for endpoint for the endpoint problem. So why is this happening? Well, first of all, we can easily see why the positivity and the polytope captures locality. So what does locality mean? If we go back to any of these pictures, one of the most primitive things is that if we have 2 chords that cross, that means that the corresponding faces cannot meet in the polytope, because the only faces that meet have to correspond to compatible chords. So that's the 0th order job, is that the polytope is keeping apart the facets that correspond to chords that cross. So how do we see that? Well, we see that in the following very simple way. It's very easy to see that given this wave equation, the wave equation is defined by one of these small meshes. This lattice wave equation is defined by one of these small meshes. But in fact, if you take any arbitrarily far apart points, any points past, future, left, and right, just by the analog of Gauss's law is just tells you that the sum of x past plus x future minus x left minus x right is just the sum of all the charges inside. Okay, so if you shrink that picture down to zero size, as usual, you go from the integral form to the differential form of Gauss's law. But the lattice version of that is that starting from this basic mesh, you can talk about an arbitrarily big mesh, and it's exactly the same statement. X past plus x future minus x left minus x right is the sum of all the charges. And so if I have two chords, ij and kl, that cross each other, then I write down, then they satisfy this formula that x past plus x future minus x left minus x right is the sum of these c's. Remember, since all the c's are positive, the sum is also positive. And that tells me that if I put x past to 0 to live on the facet ij, then I cannot also put x future to 0. Because if I do that, I'd have the sum of two negative things equal something positive, which is impossible. So that's the way in which the positivity tells us that the facets of crossing chords can't meet in the polytope. Okay? And there's a two-line argument that I won't go through in detail now, since I'm already running extremely long, that actually tells you what the facet looks like. If you put a given point inside this, if you put an x inside this kinematic spacetime to 0, then there's a very simple two-line argument that tells you that what it looks like is the direct product of two smaller of the problems in two smaller triangles. So you literally see that the facet is the direct product of the facets for the two smaller problems of the polytopes of the associahedra for the two smaller problems on the left and on the right. Okay, so that's so all of this just follows trivially from this starting point that we're asking for a wave equation, the sort of the solutions of this discrete lattice wave equation with demanding that everybody is positive and demanding that the sources are positive as well.
Can I ask just one question? Sorry, Nima, at this point. That constant, positive constant C you chose for each causal diamond could have been different on each causal diamond?
Yes,
I mean,
yes, it could be anything. It could be anything you like. Okay, so, and that's actually, that's one of the quite non-trivial things, that no matter what you make it, the shape is always the same. Okay? You'll move things around, you can make things longer or shorter, but you'll never change the sort of pattern of how things meet. Again, that's not true of random polytopes. If you take a polytope where you take a bunch of linear, 3x plus 4y minus 7z is greater than 17, and you write down a bunch of equations like that. If you change the right-hand side in general, you will change what the shape looks like. But what's really interesting here is that so long as these c's are positive, always exactly the same shape.
Thank you.
All right. So again, in the spirit of the vignette, I'm not going to tell you how we. Here, I just told you where the shape came from. I'm not going to tell you in detail how you really get an amplitude out of this. But let me tell you what again some of the key words are. So the amplitude is most primitively in this picture a certain differential form that lives in the big kinematic space. So again, this is our canvas. It's just this kinematic space of xij's. That's all we have, right? So in this space we have a certain differential form, but it has the property that when you pull it back on the support of this discrete wave equation, it becomes a so-called canonical form of this polytope. Now, canonical form is a form that has logarithmic singularities on the facets of the polytope of all codimension. Logarithmic singularities means that it locally looks like the wedge product of a bunch of d log of n coordinates if it's an n-dimensional space. Furthermore, this manifests that this form has a certain symmetry. It's a hidden symmetry known as that we call projective invariance. This hidden symmetry has many consequences. One of them is that the amplitude, if you go off to infinity in a particular direction, the amplitude dies faster than you would expect from any Feynman diagram individually. And indeed, every Feynman diagram individually breaks this projective invariance. Only the sum of all the diagrams actually has it. And that is again a fact that's made completely manifest by the existence of the polytope. This projective invariance is a hidden symmetry of the trace phi cube theory that is in many ways the analog of the dual conformal symmetry of n equals 4 super Yang-Mills. But here seen in just this dumb old trace phi cube theory. I never thought that these dumb scalar theories would ever have anything hidden in them, but they do. And this fact also shows up in that one way of calculating these canonical forms of polytopes in general is to triangulate the polytopes into simple pieces and then add up the very simple answer for each triangle. There's one very natural triangulation of this class of polytopes that directly gives you Feynman diagrams. This is one that hides this projective invariance term by term. But there are other triangulations that are possible that turn out to be much more efficient than Feynman diagrams and also make this symmetry manifest term by term. You can again think of these as the analog of BCFW for this phi cube theory. It's not literally BCFW, but it's the analog of BCFW. BCFW exploits the fact that Yang-Mills theories at tree level and at loop level, n equals 4 super Yang-Mills, have dual conformal symmetry. The analog of dual conformal symmetry is this projective invariance. In n equals 4 super Yang-Mills, what manifests this dual conformal symmetry, what manifests the full Yangian symmetry of the theory, is the connection with the positive Riemannian and the amplituhedron. Here, what manifests the projective invariance is the connection of the amplitudes interpreted as the canonical form of the corresponding associahedra. And there are also other methods to get the form without any triangulations at all, one of which I will talk about in a moment.
Sorry, Nima. So just to understand it, you're saying, so now given this polytope, you can associate some kind of a canonical form.
That's right.
When you restrict to every face, it has some log singularity.
That's right. Yes, exactly. And in fact, there are many ways of describing what this form is. One of them is that if you take the polytope, there's a notion of the dual of a polytope. And if you literally calculate the volume of the dual of the polytope, it's the thing that we're after. So the amplitude is literally the volume of the dual of the associahedra in this case.
I see. And just very quickly, the projective invariance is a statement about some kind of scaling. What?
Yeah, let me. Since you have kindly said that you have a similar notion of time as I do.
Yes.
Let me. If you don't, maybe I can explain it. It is very simple. It is very simple. But let me.
Thank you.
Can you see my screen?
Yes.
So let's say that let's go back to 4 points. Okay. Mm-hmm. So at 4 points, this is what we would say the amplitudes, right?
Oh, AdvancedStudies slide.
Oh, sorry, you don't see my slide. Hold on a sec. Sorry. Do you see this now?
Yes.
Yeah.
Okay. Great. All right. Good. Okay. Now, what we're saying is that instead of thinking about a function, you should think about a form. So I'm going to think about a form, which is just a one form in this case, which is going to be ds over s, okay, and then dt over t. And now, most naively, you put a plus sign there, okay? But we say that no, actually, you have to put a minus sign. All right. Now, what's the difference between the plus and the minus sign? Well, with a minus sign, this form is actually the d log of s over t.
Okay.
You see, it's only a function of so it's invariant under st goes to any alpha of st times st. Okay, so that's a sense in which it's projectively invariant.
I see.
Okay. Now here it looks a little bit trivial, but you can already see if you go to 5 points. Now we have sort of 5 diagrams. And so you could have something like d log, s12, d log s123, plus or minus the next one, right? D log S23, D log S234, plus or minus, okay? And now if you look at it, if you demand that the forms are invariant under all of these S's go to alpha of S times S, if you demand projective invariance, you can check that there are more equations than unknowns, okay? So it's not at all guaranteed that it works, but you find that it is possible to choose the signs such that the form is projectively invariant. And as you go to higher points, it's more and more not non-trivial. You have many more equations than the unknowns, but remarkably, it's possible to choose the sign so that the form is projectively invariant. Okay. The conceptual reason for that, or for the fact that it's possible, is exactly that there is this underlying polytope. Okay. And the reason is that each one of these forms has a singularity, both at 0, if you like, when the argument is 0, and as well at infinity. However, the polytope, by construction, the only singularities that it has are on its boundaries, and it can't have any singularities at infinity. Okay? So if I were to give you the simplest example of a canonical form, if you take an interval, let's say, and here's x equals a and x equals b, and you want to write down a one form that has logarithmic singularities on at x equals a and x equals b, then I might write down dx over x minus a and dx over x minus b. But again, it's very important to have a minus sign there, because if you had a plus sign, this would also have a singularity at x equals infinity. Okay, it would have a residue at x equals infinity. We don't want that. We want something that only has singularities on and only on the boundaries of this space. And so if we do that, then we'd get dx over x minus a minus dx over x minus b. Okay, so that's the symmetry of projective invariance. But finally, you might ask, well, I don't care about this form. I care about the amplitude. And you see, and this is where the story of this polytope comes in, and I'll draw it already at 4 points. So at 4 points, I have S and T. I have this form, which is ds over S minus dt over t. How do I get the amplitude out of this form? Well, what I'm supposed to do is constrain this on the solution of the wave equation, which in this context is of that discrete wave equation, which in this context would say S plus T is a constant. That's like my mesh constant in this case. So let's say I take this form. So S plus T is constant. There it is. If this constant is positive, even, and I ask that S and T are positive, they even intersect here. So there's my interval that I was talking about before. But what happens if I take this form omega and I restrict it to S plus T equals constant? You see, then what I get is ds times 1 over S plus 1 over T, okay, where T is equal to C minus S. Okay, but I can make C anything I like, anything positive, but still I can vary it. Okay, so there's the amplitude right there. Okay, so the amplitude is actually what you get after you pull back the form to the solution of the wave equation. The minus sign here disappears; it turns into a plus sign. But the fact that the underlying form didn't have any singularities at infinity is reflected in the fact that this amplitude is better behaved as you go off to infinity than you would naively expect. And in particular, if you naively go off to infinity in S and T, then you would think that this thing is going like, 1 over S or 1 over T. But of course, if we write it as S plus T over ST, and we live on S plus T as a constant, then as we go off to infinity, keeping the C constant, this thing is going like 1 over S squared and not 1 over S. So it's dying faster than you would naively think. And again, that statement is ported up to any n. Okay, so that's the sense in which it's analogous to a BCFW that also, and dual conformal symmetry that also tells you there's a better behavior at infinity than you would naively think. That's made obvious by the connection to some geometry. In this case, the form has this projective invariance, and the amplitude is related to the form in this interesting way, which implies that the amplitude is better behaved at infinity than you would naively think, but which is made manifest by the presence of the geometry.
I see. And really, thanks for that beautiful example. Nima, it seems the fact that your wave equation that you were imposing didn't care about the exact values of those constants, that you could rescale them, is closely tied to why you get this particular projective invariant form and so on, or no?
It's no, that they're not exactly the same thing. Although the fact that it is projectively invariant ports to the projective invariance is more fundamental. It implies that you can there's two facts. One of them is the overall rescaling by any function of S and T, but it's just one overall rescaling. That's one fact. There's a second very non-trivial fact that no matter what you make these constants, you never change the combinatorics of the shape. I mean, you change the actual shape, these parallel sizing it further apart, closer, and so on, but you never change what the pattern of how they meet. And that's a very non-trivial fact, which is made manifest by this picture. Guys, I don't mean to, I wonder if what we should do, since I've gone on so long, should we maybe stop and clap or something like that, so that people who want to go can go, and people who want to stay to hear about the strings can stay.
No, but Nima, usually we do go for about 2 hours. So I think.
Oh, wonderful. Great. I shouldn't feel bad then. Okay. Very good. Excellent. Very good. Very good. Yeah.
Just one question. So what is in general the relation between the form and the amplitude itself? So here you gave an example, but
it's always the same. It's always that you have the form that lives in the whole kinematic space, and you always pull it back to this to a natural subspace.
But one-dimensional subspace, so that you only have
it's a codimension exactly the sort of difference between in general at n points the kinematic space is n times n minus 3 over 2, so roughly n squared dimensional. Okay, whereas the number of poles is n minus 3. Okay, so this is a very high codimension thing that's sitting there. So there's this, but it's a plane. So it's a plane. It's an n minus 3 dimensional plane that lives in this n minus 3 over 2 dimensional space.
Okay.
It's just that n minus 3 dimensional plane has a name. It's called solution of the wave equation. Okay. So you see that what the wave equation is doing is just imposing linear constraints on all these x's that knocks you down to live on this plane.
Okay.
Okay. But the sort of little miracle is that it's possible to put plus and minus signs on the form such that when you pull back to the space you get the canonical form. And the way to get it, the way to get the sign is that if you take upstairs sort of d log of any bunch of variables that correspond to planes that meet at a vertex, then you just weight it with the sign of the determinant of the normal vectors there. Okay, so that's guaranteed to give you something which pulls back to the form and is projectively invariant.
Thanks.
Okay, all right. So let's maybe go back. Okay, so now that was a story just at tree level. And as I've said a few times, our main sort of project over the pandemic has been to figure out how to extend these to all loop orders and to all to every order in the genus expansion. So the claim is the following. And of course, there's a number of qualitatively new things that happen. If you maybe invite me back sometime after this talk, I'll be happy to give a more dedicated talk on the whole story.
Nima, I'm really sorry to, please excuse me to stop you again, but so just to get it, so you have this wonderful then form you can define which has log singularities, and then the last thing I didn't get, which is the physical amplitude is defined as some kind of integral of this form, is it?
No, it's not the integral. No, it's even simpler than that. You don't integrate here. You don't integrate the form. It's just that the amplitude is when you pull back to the surface, there's just the trivial volume form on the surface, and so you just factor out that volume form, and the amplitude is the function which is left over.
Front of it. Okay. Yeah. Okay. Thank you.
And as I said, there's many ways of saying this. One of them, which just directly gives you the function, is if you take this associahedron and you take its dual and you compute its literal volume, that's also the amplitude.
It's the volume of the dual. Okay, thank you.
It's the volume of the dual. Yeah. All right. So if we talk about general Feynman diagrams, if we talk about this trace phi cube theory at any order in the one over n expansion, we know that we can think of it as drawing the Feynman diagrams on surfaces with of general genus with punctures corresponding to closed loops, closed color loops, and boundary components with marked points corresponding to all the different traces in the expansion. So all the single trace guys would only have a single boundary component with n marked points. The double trace guys with the n1 and n2 pieces of the trace would be two of these little circles with n1 points and n2 points on them. And we can plonk those down on any genus surface with any number of punctures. Okay. So what we found is that so this is some sort of new fact about Riemann surfaces, or just about surfaces, is that there's for every homotopy class of arcs on the surface. So that's what we had on the disk. There's no topology to speak of. So all the arcs just corresponded to things that connected pairs of points. Well, in general, there's for every homotopy class of arcs on the surface. So we're going to associate a polytope that we call a surfacehedron with any surface S. Okay. For any homotopy class of arcs on the surface, there's going to be a facet. In general, there's infinitely many of these arcs, and that begins already with the annulus. So if you draw the annulus, you imagine a bunch of points on the outside, maybe some points on the inside. Then we have arcs that can just wind around the inside any number of times. And so there are infinitely many facets. And so that's one of the challenges, was to figure out how to deal with this infinity. And this polytope is a very interesting fractal structure in general. I'll show you some pictures in a moment. But what is the point? Just like we saw in the associahedron, what this polytope does is the facets capture all the pinchings of the surface. So in the case of the disk, if we took a given arc X and we imagine pinching on that arc, we get the product of two simpler surfaces. Well, that extends. If we imagine we have some inner puncture, and I take this surface here, and I can imagine pinching on that guy, then that's like cutting the surface open and introducing two extra points here in the middle. Okay, so sometimes it looks like factorization into two simpler pieces. Sometimes it looks like still one component, but with some extra points. All right, so for every facet. So for every arc, there's a facet, and on that facet, the polytope looks like the direct product of the. It looks like what it's supposed to look like, either a product or whatever it's supposed to do to correspond to the corresponding pinching of the curve on the surface. Right. Now, one of the fascinating things that we found sort of very early on is that even though when you just draw the Feynman diagrams for the trace phi cube theory, the only arcs that you care about that sort of correspond to the, if you imagine these as duals of Feynman diagrams, these are the arcs that would correspond to the propagators in the picture. That even if you wanted to even if you began just by thinking about those guys, that the polytope tells you that it can't close, that the polytope has some holes that are only filled in, and you only get a complete polytope if you also think about closed loops on the surface. Okay, so you also have to talk about loops like this. Now, these do not correspond to things that we would associate with the propagators of the trace phi cube theory. There's something else, but they have the property that on these facets, you also factorize in some appropriate way. Again, as you'd expect from the picture, that if you take this sort of delta closed loop and you pinch it, you should get now the product of two surfaces where you've added a puncture where the pinching happened. Now, if this looks familiar, this, of course, is exactly the way we, of course, these pictures are very familiar in string theory, and this is also exactly the way we discovered closed strings in one loop open string diagrams in string theory. And indeed, these delta facets are the sort of polytopal avatar gravity in this picture. Again, but there's no strings here. There's no alpha prime. This is just some primitive fact about the combinatorics of arcs on surfaces, and these surfacehedra. And I don't have time to.
Yes. Nima, can I? So in the previous slide, I didn't understand the bottom. Yeah, can I go to the? Yes, this bottom left diagram. Oh,
this one. Yes.
What does it? I mean, can you say? Can you explain that again?
Yeah. So this is if maybe if you imagine what this dually looks like. Let me.
Nima, just to back you up even further, sorry. I mean, so far you were talking about polytopes and so on. I understood, but are you talking? I mean, what is the annulus now? Is it something else? I mean, I got confused by your. Sorry.
Oh no, sorry. Now I'm talking. Yeah, I'll explain that in a moment. I'll explain that. I'll explain that just in a second. Okay. So let me first say. It's what you get if you imagine taking the surface and sort of like cutting along this line. Okay, so if you imagine sort of cutting along this line, what
yeah, I can't see what you're drawing.
Oh, sorry. I keep not doing that. Can you see now?
Yeah.
All right. So first, this is just a statement about a surface, and then I'll give you the like physics. But this will also help with Sandeep's question. I said it quickly. So if I take this thing and I cut, imagine I take the surface and I literally cut along this. Well, if I sort of cut along it to imagine that I'm cutting it open. So cutting it open is like adding 2 extra points here. Okay. So, but let me now answer Sandeep's question, which will also give you a good. So imagine that we look at this. I have a puncture now here. So let's look at this triangulation. So this is a triangulation now, not of the disk, but of the disk with 1 puncture. Okay. Now, what is the dual of this diagram? Okay, so this is a 1 loop diagram.
Okay.
Okay. And so, what does this correspond to? So, what does cutting this guy correspond to? It corresponds to putting this intermediate propagator on shell. It corresponds to putting this inner line on shell.
I see.
It's like cutting that guy open. But you see, cutting this guy open is just as if I'm doing something at tree level, but with 2 extra points. It's called the so-called forward limit. Okay.
Yes.
Right. So I had one. So I had 1, 2, 3, 4, but now I've added some like A and B in between 4 and 1. Okay. So that shows that, and indeed, I mean that's so if you have if we talk about 1 loop diagrams, you know, for this kind of theory, I'd have things like this, right? I'd have all kinds of things. Right, these are all different 1 loop diagrams, and some of the factorizations, like this one, this would just factorize into like a 3-point 1 loop on one side and 3-point on the other. That's one kind of factorization. And in the picture, sorry to keep switching colors here, but if something like that would correspond to I don't know, cutting on something like that. Okay, if I cut on something like that, then I get then the puncture is left on one side and I have a 3-point on the other side. Okay, but I also have cuts that cut one of these internal propagators, and that corresponds to one of the ones that I just talked about. That corresponds to like cutting that guy open, and cutting that guy open now turns us into an effective problem with 6 points, not 4. Okay. So I get sort of I get 2 extra points compared to what I had before in between there.
Okay, thank you.
Okay, and so that is the claim. The claim is, so what if I say it in the language of surfaces or I say it in the language of diagrams, that just like we saw at tree level, that there's a polytope whose vertices are all the Feynman diagrams and whose facets are all the partial factorizations, right? The claim is that that's true completely generally. Okay? That's true absolutely, totally generally at every order in the 1 over n expansion, for every genus surface, at every order, at all loop order. But there are some interesting novelties, which is that in order for the whole polytope to close up, you also have to add some facets that don't correspond to the Feynman diagrams of the theory that you wanted to begin with. They correspond, there are some new variables too. And if you were to interpret them as poles, they would be poles for particles that have no color, that would sort of, and that would give you exactly the kind of singularities that we'd associate with closed strings being exchanged here. Can you guys see my slides again now?
Yes.
Okay, great. All right, so here are just some pictures for what they look like. This is supposed to be purely impressionistic, but just so you see, there are some actual things here. So this is a picture of the disk. This is a representative Feynman diagram with this topology. Now I'm drawing it in double line notation, and we get the associahedra. Here's something we get at one loop. Okay, so this is again, this is now the surface would be instead of for a 3.1 loop amplitude would be a surface with a puncture in the middle, and again there is a polytope associated with it, and I haven't shown it here. And again, if I had longer, we could actually go through and I could show you that every facet of this guy, there are different shapes. They correspond to either cutting this way or cutting that way. That correspond to these internal propagators, or the loop propagators, or the normal factorization propagators. And that the whole picture fits together self-consistently. So you don't need to have any external particles. This is the vacuum diagram. That the vacuum diagram would be associated with the 3-punctured sphere, and that's associated with the following sort of a beautiful shape. Here, what I've chosen to draw here are all the 3-dimensional examples, so that the ones that we can at least easily visualize. Here is the first interesting example of an annulus. And maybe this really answers your question, Sandeep. So this is the surface. This is the corresponding representative Feynman diagram. Okay, so it's a double trace, 1 loop correction in this case to a 3-point amplitude. Okay, with two traces on the outside and 1 trace on the inside here. And here already you see something interesting. You see this as a kind of infinity here, right? You see these, there are all these facets. The guy upstairs is already kind of interestingly infinite, and you probably can't see in detail, but there's a bunch of interlacing pentagons here, and they're asymptoting to the sort of hexagon in the middle. Okay, this hexagon in the middle, and that hexagon in the middle is what's associated with this, is a facet associated with this curve going around. Okay, that's this closed curve that I was telling you about before. And that infinity is associated with the fact that there are all kinds of loops going around here. Okay, there are all kinds of not just that loop, but all kinds of arcs, not just the arc that would go from here to there, but also that one that goes from here to there and winds around any number of times. If I say this much more technically and fancily, these polytopes are capturing the boundary structure of the Teichmuller space of the surface. Here I haven't said anything about hyperbolic geometry, but it's related. But there's of course the avatar that relates it to hyperbolic geometry, and not the moduli space, which is what you get by modding out by the action of the mapping class group. In this case, the mapping class group is just taking the Dane twist of the inside annulus, and I can twist it any number of times I like. But what we're talking about here is just the sort of largest object, which is the whole space that treats separately all of the chords, all of the arcs that wind any number of times. You can ask me, where is the information about that winding any number of times in the Feynman diagrams? And the answer is, it's related to the fact that there's an ambiguity in how you label loop momenta when you have different kinds of diagram. And there is a natural way of not making any choice at all, but keeping an infinite number of copies of the diagram. And that's what this polytope is capturing at first blush. You can then ask how we go from that to getting the actual amplitude that would only keep one copy of all the diagrams, and that's the analog of modding out by the mapping class group or finding a fundamental domain. And there's a polytopal avatar of that as well. But again, that's something I'd be very happy to talk about in the next time you invite me to speak, if ever. Having overstayed my welcome. Oh no, not quite so much though. You said you normally go on 2 hours, so I haven't overstayed my welcome yet. If we keep going,
so this is also the loop integration modding out by the
so far this is just even at the level of the loop integrand. In a moment when I talk about the connection, actually I probably won't talk about it, but when we talk about the connection to these binary geometries and strings, it also gives you an immediate way of doing the loop integrations. And then after you do the loop integrations, then it's a more familiar modding by mapping class group over what looks like an integral over a moduli space. Here it's already at the level of the integrand, but the analog of a fundamental domain is finding some way to just keep a finite number of these diagrams. And that's associated with the fact that I can define these polytopes with those, they're all come out from analogs of those equations that we talked about before with mesh constants with these C's. But what you can do is shut off many of the C's, and that collapses lots of these facets down to something finite. And that's the analog of that turns out to be the analog of finding a fundamental domain. We don't know in complete generality for a totally general surface systematically yet how to find a fundamental domain, but we know how to do it in examples, and we hope there's a general picture for doing it. Finally, here's the sort of, I think, one of the probably the coolest three-dimensional polytope known to humankind now. It's the shape associated just with the once punctured torus. Okay, so if I take this once punctured torus, it corresponds to this non-planar vacuum graph, and you get this crazy looking picture. And this is really a fractal now. I don't have to justify much in detail that if you think about what labels the arcs on a torus, it should be a P and a Q for any rational P over Q in lowest terms. So that means that this insane object has a face associated with every rational number P over Q. And the way it manages to do it is by having a remarkable fractal structure. Here I've projected this three-dimensional picture down to 2 dimensions. And so you start off having something that looks like this, but if you zoom in on any corner, you keep seeing more and more and more things that look of exactly the same type, such that in this shape, for example, every direction, in every slope, every rational slope, you'll actually find a unique edge with that rational slope. And the whole picture lifts to 3 dimensions because it's actually a three-dimensional space in the three-dimensional polytope. All right. So that's the claim. Is that this the connection, and therefore the canonical form associated with these surfacedra is this infinite notion of the integrand that does not make any choice over a fundamental domain. Okay, so there's a well-defined infinite integrand that makes no choice over a fundamental domain in loop momentum space, which is the canonical form associated with these polytopes. And if you we conjecture that it's always possible to shut off all but finite number of faces that would give you literally a fundamental domain. But it really looks like the cleanest object theoretically is this sort of infinite one, and that there may be other ways of thinking about dealing with the issue of the fundamental domain, which I'll come to in which is well, I'll see if I manage to say something about it. All right, so what I hope you've gotten from this second part is that there is some origin for this. So there's some pattern of how the poles come together at tree level. That pattern extends in a very interesting way to a loop order, and there are these the notion of, and these notions of positivity in the kinematic space is just the space of all arcs on the surface. and the notion of positivity in kinematic space brings these interesting polytopes to life.
So
Now I want to tell you, right.
I know you have to go on, sorry, and this is very nice, but since you've set it up so beautifully, there is no action of the mapping class group on your polytopes. I mean,
that there is, yeah. I mean, it for example, here it really moves you. The mapping class group acts in a piecewise linear way on the polytope. So, for instance, in this case, if you look at this picture where the mapping class group is pretty easy, it's just sort of winding, right? Mm-hmm. You'll see that there are these that there are things that are approaching delta kind of from the left and from the right, mm-hmm. And so there's really sort of two winding sectors: the things that wind positively and the things that wind negatively. So that's what the mapping class group does. It just pushes all of these pentagons along in one direction on one side and the other direction on the other side. But it's not a global linear transformation. It has a piecewise linear transformation on these polytopes. I didn't stress this earlier, but remember very early on here, this was our whole big kinematic spacetime, completely invariant thing, but we made some choices in how to cut out the region that we're looking at, right? I said, I'm going to look at this sort of right triangle as a way to include like ij and not ji, but I could have drawn this one too, right? There are a lot of different ones. So each one of them will give you not exactly the same polytope. They'll have exactly the same combinatorics, they'll have exactly the same invariances, but they're not literally exactly the same polytope. So there is some kind of choice in picking out a region of the kinematic space to begin with. And I've made such a choice in all of these pictures. So having made that choice actually gives you a dividing line between sort of positive winding and negative winding. And positive winding is pushing you along, coming around this side. Negative winding is pushing you along, coming along this side. But there is an action of the mapping class group, which is piecewise linear. On the left, it's pushing you this way. On the right, it's pushing you the other way.
Thank you.
All right. So what I now want to do is tell you about something else, something even more, I think, even more rigid, an even more rigid geometry that associated with the combinatorics of compatibility. And let's just say broadly again, if we go back at tree level and just summarize what we've seen, is that we can take this, we can take the disk, we talk about these variables xij associated with any accord. And then there's some sort of linear inequalities on the xij space that associated with all the picture that I was just telling you about that converts this to this pentagon. And the linear inequalities capture the combinatorics of compatibility and factorization, okay? However, as I've said a number of times, it's not 100% rigid. I mean, things depend on these constant C's that can move these things around. The shape is always the same, but the kind of detailed shape is, the pattern of how the faces meet is always the same, but the detailed shape, of course, will depend on the constants. Wouldn't it be nice if there was some way to sort of geometrically capture all of the pattern of compatibility in a completely rigid way that didn't have any kind of sort of moduli of this sort at all? And it turns out that there is. Again, there's a whole sort of conceptual story associated with this. But let me just sort of tell you what the answer looks like in the simplest case of the disk, and then we'll explore some things about it. But I at least want to tell you something that if you wanted to, you could go and play right after this talk and actually confirm some of the things that I'm telling you in real time easily. So what we're going to do is the following. Instead of looking at a bunch of linear inequalities on variables xij, with every chord, we're going to associate a variable uij. And we're going to write down the following beautiful equation, that the u for a given chord ij plus the product over all the other chords ukl all the KL that cross IJ, so all the incompatible chords, UIJ plus the product over all of the KL crossing IJ of UKL is equal to 1. Now, naively, this is, I have as many equations as unknowns, so naively, this would only have solutions in points, perhaps. However, remarkably, it gives you more. Remarkably, it gives you a variety of the correct dimension. So remember, in the case of endpoint scattering, we basically had an n-3 dimensional space. It was 1-dimensional for n equals 4, 2-dimensional for n equals 5, 3-dimensional for n equals 6, and so on. In general, an n-3 dimensional space. So remarkably, this gives you an n-3 dimensional variety. Now we next impose positivity. So we ask that all these u's are positive. This point is really remarkable. I just want to stress it again. It's not at all obvious that these equations give you an interesting, a non-trivial space of solutions, but they do give you a non-trivial space of solutions in a variety of correct dimensions.
So sorry, yes. Nima, and you can just ignore it, but I only know about algebraic varieties and so on. What does this mean when you say it's a variety?
That's exactly that. It's an algebraic variety.
Okay.
It's just a bunch of polynomial equations. Right?
Okay.
Yeah.
Okay.
It's just an algebraic variety.
But it's therefore some non-trivial space, not just a bunch of points.
Exactly. That's what's not non-trivial. That it's a non-trivial space and not just a bunch of points.
Okay.
Right. Okay. So
sorry, Nima, this equation has real roots. I mean, this equation has real roots because now this is not linear. This is a polynomial.
Right. So I'm saying, even before saying anything about roots, I'm saying that this equation parameterizes an n-3 dimensional complex variety in general.
Complex, okay.
Complex variety. Everything is if everything is complex, it's just a complex variety in general. But it's a complex it's a complex variety. Okay.
Okay. Thank you.
But now I can restrict myself to the variables being real and positive. Okay. And so that's where positivity comes in. So I'm going to ask for these u's to be positive. And notice that if the u's are positive, these equations then immediately tells you that the u's will also be less than 1. Okay, because the sum of positive things equals 1. So they would also have to be less than 1. And now notice a sort of beautiful thing about this, that if a given uij goes to 0, if I think of that as sort of being a boundary somehow. So if a given uij goes to 0, because it is, I'm asking them to be positive, then this equation tells me that all the u's for the crossing chords go to 1. Okay? So remember, that was what we were seeing before from the linear inequalities for the polytope, is that if I had two facets that corresponded to non-crossing, that corresponded to crossing chords, the facets couldn't meet. That's what the polytope was doing. But here we have something even more rigid, that if a given u goes to 0, it's not that the incompatible chord can't meet it, it just goes to 1. They all go to exactly the same thing. They all go to 1. So it's completely binary. Okay, we get a binary geometry of the compatibility combinatorics. I should say that these equations were written down in the early days of the dual model, and were rediscovered by Francis Brown and some beautiful work of the mathematician at Oxford, Francis Brown, in the mid-2000s. And we've been very excited about their importance and have been exploring them for the past number of years. And again, what we've been doing, especially over the past number of months, is understanding what the generalization is of these equations for any surface. Okay. But I want to tell you a little bit more about them. So notice that these are some equations. They have nothing. There's no actual picture of a surface. There's no two-dimensional surface here. It's just, there's no metric on the surface. There's nothing. It's just a completely topological fact about the surface, if you like, just crossing of chords. But these are very nonlinear equations. And so what I keep stressing that it's very non-trivial that they have solutions. And so there's a variety of ways that solutions to these equations can be given. Here's one of them. Okay, so let's say we talk about the case of 5 points. The case of 4 points is a little bit boring, although maybe slightly interesting already, because you would say that the equations are u13 plus u24. let me just maybe write these down. Just because. Oops, no, not that. Sorry. Oh, here we are. Yeah, see, here we just have like, here I just have two crossing chords. So the equations are u13 plus u24, which crosses it, is equal to 1, and u24 plus u13 that crosses it, which is 1. So you see it's two equations and two unknowns, but it happened that they're the same equation. Okay, so that's why all I get is u13 plus u24 equals 1, and so that's fine. So that's a nice one-dimensional space. Okay. So let's now move on to the here we go, to n equals 5. So now there are 5 equations that you can think of as just being u13 plus u24 u25 equals 1, and then you just cyclically rotate everything. So those are 5 equations. Oops. Sorry, guys. Okay, those are 5 equations. But you can check that these equations are solved in terms by now really thinking about the hyperbolic geometry inside this space. So if you now really think that that this is a Poincare disk, or I can map it to the upper half plane, okay, then let me draw it in either side. Remember, geodesics looks like semicircles here. So just draw the semicircles. And so these are the boundaries, 1, 2, 2, 3, 3, 4. So you just really imagine everything here is geodesic. And the claim is that these u's are very simply related to, they're not literally, but by a very simple change of variable, they're related to this geodesic distance. So u13 is this geodesic distance. u24, u25 are these corresponding 24 and 25 are these corresponding geodesic distances. If I draw the points in the upper half plane, similarly, there are just certain geodesic distances associated with the corresponding semicircles. And in general, at endpoints, there's a formula for the uij's in terms of the cross ratio of the z's. Okay, if you imagine I just have a bunch of ordered points either on the plane or on the circle, it's a particular cross ratio made out of the points I and j and their two neighbors I-1 and j-1. Okay, so these are the fundamental equations. These sort of binary equations are the fundamental equations, but you can check that they can be solved by associating them with hyperbolic geometry. Okay, and a picture of a bunch of ordered points and thinking about these cross ratios and so on. So of course these are variables that look a lot like what we're used to seeing on the worldsheet. Okay? But this is in fact just one representation of solutions to these binary equations, and there are others. It's these others that are connected with some of the other conceptual things that I mentioned early on. Cluster algebras, quiver categories, and so on. So let me give you a very different seeming, of course, they end up being closely related to each other, but not totally trivially. Let me give you a very different seeming way of solving these equations. There's no picture of a worldsheet or a disk or a Poincare disk or anything like that. I just explicitly realize all these u's as simple ratios of polynomials, very simple polynomials. So you can check that this is a parameterization in terms of just two variables, y1 and y2. This is supposed to be a two-dimensional space. And indeed, you can check that this set of u's satisfies the u equations. And also such that what's nice about this representation is that when these variables y's are merely positive, they guarantee that the u's are between 0 and 1. So you can think of this as a positive parameterization of these uij's. Again, these are just ways of solving these equations. The equations are the most invariant thing. there are these equations, and then you can find parameterize the spaces of solutions for them in various ways. One way makes it, one way relates it to hyperbolic geometry in the worldsheet. Another way pulls out these sort of interesting polynomials, and I haven't explained to you where they come from, but there's a picture involving quivers and counting sub-representations of maps associated with quivers that gives you these polynomials with no picture whatsoever of anything like a worldsheet anywhere around. Okay, so there's various ways of solving these equations, but the equations are the most invariant thing. Now, also, this binary geometry is very closely connected to the polytopes that I was telling you about before. And in fact, there's a fact about the polytopes which is telling you exactly about these, something about these polynomials that show up in this interesting parameterization. So you've never heard of this binary geometry business, but if we go back to the picture that I told you about for the pentagon, and here I'm sort of drawing what I'm drawing in a little more detail what the pentagon looked like parameterized by those mesh constants C, C prime, and C double prime, telling you where these various corners are as a function of C, C prime, and C double prime. Well, this tells you that you can actually view this pentagon as being in a precise sense a sum of simpler pieces. The sum here is known as the Minkowski sum. And the Minkowski sum of A and B is just the sum of all the vectors in A plus all the vectors in B. Okay, so if you have any two sets A and B, the Minkowski sum of A and B is just the sum of all the vectors in A plus the vectors in B. So this is saying that this interesting, that our interesting associahedron polytopes at tree level are actually a sum. They're a Minkowski sum of simple pieces. And why would you expect that? Well, remember, we are solving something like the discrete wave equation with sources. And whenever you have a linear equation with sources, it's useful to have the Green's function picture. To get the solution for general source, it's useful to think about the solution for delta function sources and then add them up. Well, in this case, the analog of delta function sources is to turn on only one of these mesh constants and turn off the other ones. And if you do that, if you only turn on C, let's say, and you turn off C prime and C double prime, you'll see this whole picture just collapses to that interval. Okay, so the shape that you get if you only turn on C is just this little interval. If you only turn on C double prime is that little interval. If you only turn on C prime is this little triangle. And so the whole pentagon is this interesting Minkowski sum of this interval, that interval, and this triangle. And those shapes, interval, interval, triangle, tell you these polynomials, exactly these polynomials that we saw in the previous picture. Okay, you can think of this, if you think about this two-dimensional space, this x direction being labeled by y1 and the y direction being labeled by y2, then you can record the corners of these little pieces just by with an associated polynomial. So the point 0 there would just be a y1 to the 0, y2 to the 0. The point here would be y1 to the 1, y2 to the 0. So we get this simple polynomial. In general, these are known as the Newton polynomials associated with a polytope. In this case, they're extremely, the monomials simply record the integer vertices. Okay, so summarizing, this is what we got from our polytope beforehand. So this was the story from the second part of the talk. But there's a fact about these polytopes, which is fascinating, that they're naturally expressed as a Minkowski sum of pieces, and the Newton polynomials associated with these pieces are exactly the objects out of which these U's are built. Okay, so and again, if I told you more about the rather than this vignette, if I told you more about the associated story, there's an absolutely precise way of going from these polynomials to the U variables. Yes.
So, sorry, Nima. Now I got a little confused because the polytope story was a part of the tree level diagrams, planar diagrams, right?
Yep.
Then I thought we moved to a higher genus or non-planar diagram.
No, they all had polytopes. So all of those things had polytopes associated with them. So any genus, anything that's what all these fancier surfacehedra pictures were about. Okay. Now I've come back to a tree level. But I'm telling you something different about. So I'm now telling you something different even at tree level. Saying if we go back to a tree level, and we even go back to our squares and our pentagons that we saw before, associated with 4 and 5 point scattering at tree level, that there's something even more rigid associated with the see, what we already saw was that these polytopes capture geometrize the combinatorics of how the poles can come together, right? That was the whole point. Is that there's a shape, and the shape captures the pattern of compatibility of the chords on the disk. Right. And in general, there's something like that for any surface. Now I'm saying that there is a nonlinear shape which does exactly the same thing, sort of even more rigidly, because everything just is between 0 and 1. Okay, so now there's a nonlinear shape, and the nonlinear shape is what you get just by writing these simple equations: u plus the product of all the u's equals 1. But all the product of all the crossing u's equals 1. Okay, and the claim is that this can be solved in a variety of ways. So it can be solved by recognizing u's as cross ratios of points. And that's a path that connects it to the world sheet. It can be solved in other ways, just by recognizing the u's as interesting ratios of polynomials that sort of positively parameterize these solutions. And the second way of thinking about things is intimately connected, it turns out, with that linear way, with the polytopal way. So I've told you something more rigid, more nonlinear, sort of more remarkable seeming, that this nonlinear binary realization exists, but the binary realization and the polytopal realization are intimately related to each other. And in fact, once you know the polytopal relation, you know a lot about the binary relation. In this case, at tree level, you in fact know everything. Once you know the polytope, you know everything about the binary realization. Okay, so now, given this binary geometry, there's something that you can do with it, which is motivated, if you like, by the Euler beta function to begin with, but it's something that you can actually do for a large class, with essentially infinite class of polytopes that has nothing to do with this whole story, but what you can then specialize to this story. So I'm just going to tell you the sort of specialization to this story. So remember, we have this set of coordinates, these y's, that give us a polynomial parameterization of these u's. So we have u's that are polynomial, that are ratios of polynomials of these y's. So what we're going to do is take this very simple form in all of these y's. Okay, so remember, the y's naturally go from 0 to infinity, so we're going to have a form that has singularities at 0 to infinity, just this d log form, d log y1 through d log yn. Okay, we're going to integrate this form from 0 to infinity, and let's say we just did that. Well, of course, this thing diverges. This thing diverges both as the y's go to 0 and they go to infinity. But this divergence is going to be cured by multiplying by product over all the chords on the surface, product of x, of the u variable associated with x to the power of alpha prime x, where now this x is playing double duty, both representing what the chord is, as well as representing what the actual, remember, that's the xij variable, the actual kinematic variable. Okay, so this is a regulator for every boundary where u sub x goes to 0. So in every boundary where u sub x goes to 0, I could get a divergence from these integrals, but this is going to save it. Okay, these positive powers of the u of x are going to regulate it. And it's an n-dimensional integral, so it could have, it could in principle have n of these u's go to 0 at once. And so we're going to put an alpha prime to the n out in front of the whole thing. So alpha prime obviously is going to have units of a length. It looks exactly like a string length, and we'll get the particle limit as alpha prime goes to 0. Now, what's interesting about this expression, of course, in a moment, we're going to see that at tree level, this is exactly the Kobe-Nielsen formula. Okay, so this is literally exactly the Kobe-Nielsen formula. It's a repackaging of the Kobe-Nielsen formula in a way that you don't ordinarily see, and it's a repackaging that's also useful because it exposes all the singularities in the Cohen-Nielsen formula in a way that, in the conventional ways of doing things, would involve blow-ups and some more detailed analysis. Okay, but this is a way of presenting the tree-level string amplitude in a way where all the singularities and all the factorization properties are sort of completely manifest. And incidentally, this is the reason why these equations were first introduced in the very early investigations of the dual models in the 1960s. Okay, so but I want to tell you what's remarkable about these equations. You see, this is going to have the following property: as some x goes to 0, as some xij goes to 0, I'm going to get a pole. I'm going to get a pole because I'm no longer regulating that part of the integral. So that's so I'm clearly going to get a pole. But the residue on that pole, even at finite alpha prime, the residue on that pole, precisely because when a given u of x goes to 0, all of the incompatible u's go to 1. That means that that the residue on that pole will be precisely equal to the product of the amplitude as defined in this way on the left and on the right, even at finite alpha prime. That's the magic of the binary property. That as a given u goes to 0, the incompatible ones go to 1, and so the dependence on all the xij's that involve the crossing chords disappears, and I just get a product of the amplitudes on the sort of left of the factorizing surface and on the right. Okay, so that's what's sort of invariantly interesting about this class of integral. All right, let's begin by looking at how this works for 4 points. And remember, here we had u13 and u24. They just have to add up to 1. And so here is a positive parameterization of them where you just write them as y over 1 plus y and 1 over 1 plus y. And clearly, as y goes from 0 to infinity, these u's are less than 1, and they satisfy that u13 plus u24 is equal to 1. Well, if I shove it into this formula, now I just have the integral dy over y. Here's u13 to the alpha prime x13, u14 to the alpha prime x24, and that's just gamma gamma over gamma. This is exactly like the Veneziano amplitude. Well, except it's not tachyons here. It's literally just sort of a massless scalar theory. So this is as alpha prime goes to 0, it reproduces what we had before in the field theory limit.
Nima, sorry,
Yeah.
one question. I mean, here you didn't put in string theory, right? But why is it that you got exactly the Veneziano amplitude? I mean, is there some choice that was made?
No, there's really no. And in fact, I mean, this is part of what I'm coming to is that here we're even only talking about scalars, right?
Yeah.
Now there is, and it's non-supersymmetric. So there is no known string background that literally has this model in it. Okay, so so there's a question that we still don't fully know the answer to, is what exactly are these amplitudes? Okay, so and one maybe I can come back to this in 2 slides when there's a few more things to say about it. But indeed, I mean that's part of the interesting thing. Nowhere here was there a world-sheet conformal field theory. No, no vertex operators, no correlation functions, nothing, right? We're just saying that there's something. We're saying this, that the sort of invariant content is that that not only is the compatibility of poles captured by Polytope, it's captured by this binary geometry, and that fact then immediately suggests this natural class of integrals that look like the integrals we see in string theory. Now, it could be that this whole story is really about the kind of pole structure, and the pole structure is universal for any theory. So it could be that once we go back and figure out how we have to add things in order to talk about things with interesting numerators, Yang-Mills, gravity, things with polarization vectors, and so on, then that will start looking more like what we would literally get from string theories. And probably if we demanded, we could ask. You see, here we're guaranteed that we get sort of correct factorization on all massless poles, but it could be that if we force correct factorization on even all massive poles, that we'll start getting some extra consistency conditions. And maybe in this way, there'd be some sort of more bottom-up way of really sort of deriving the consistent string theories. Okay.
I mean, I asked because a priori, any large N gauge theory would give rise to an amplitude which would have all the nice properties, right?
Right.
Unitarity, and so that would not have such a simple formula, but it would still admit a limit in which
right. True. I totally agree.
So much richness in this space of amplitude.
Right. Well, and so it could be that there's sort of more general things to do here than putting powers. Maybe that's where the choice is. The sort of choice that we just put powers here is maybe where we're putting in something like a free CFT in the usual way of thinking about the world sheet, right? That's so the connection between, as I said, but if I say more, well, let me maybe I'll come back to this point in 5 minutes. Okay?
Yes.
So, sorry, but I mean, just to say, it seems it's the pole structure and the particular way you chose through powers to soften the divergence.
Exactly.
Right?
It's exactly. So that's exactly right. I chose this particular way to soften it. Now, but as I said, this particular way of softening it is actually, there's something pretty canonical about it. I mean, you didn't need string theorists to talk about this. Euler was doing this 200 years before string theorists were doing it. Okay, so there's and Gelfand and friends were generalizing this in the 1980s for totally separate reasons. There is something canonical about the powers. But I mean, there's something especially canonical and simple about them. But could we do more general things? Likely so, and maybe that's the way that we could connect to more general theories. Okay, so but I want to give you some. I want to give some picture for why it's sort of guaranteed that these things are going to match the field theory limit as alpha prime goes to 0. And of course, as I said, they really are directly just a rewriting of the usual Kobe-Nielsen formula. Okay, it's a repack. So if you think about the usual, let me just say this now. I didn't have a slide for it. If you think about the usual Kobe-Nielsen formula, here, let me write something about this. Oops. If you think about the usual Kobe-Nielsen formula, it would look something like dz1 through dzn, then there's some mod SL2, then we'd have something like a z1 minus z2, these cyclic differences, and then we'd have a product over ij, zi minus dij to the alpha prime pi dot pj. Okay, so but these z's have to be ordered, like z1 less than z2 less than zi. Okay, so there are two things going on here. First of all, the z's are being written in terms of some function of these y's, and the purpose of these y's is such that it guarantees that they're ordered. So it's not quite, but it's a little bit like saying you put z1 equals 0, z2 equals 1, z3 equals 1 plus y1, z4 equals 1 plus y1 plus y2, something like that. Okay, so if you do something like this, it's guaranteed that we'll have z1 less than z2 less than z3 less than z4, etc. Okay, so that's the first part. That's a relatively straight. Well, they're both relatively straightforward. But that's a positive parameter. That's a positive parameterization. Okay. Okay. But now comes the sort of the second and more interesting part. Is that, you see, when we write this zij to the alpha prime pi dot pj, and you want to know, well, where are the poles? Where are the poles? Where are the poles of the answer? You see, there's quite some sort of repackaging. You see, the poles are not when pi dot pj goes to 0. The poles end up being when pi plus dot dot plus pj minus 1 squared goes to 0, right? This is where the actual poles are. And in order to see that, it's a little bit of work. You have to sort of gauge fix. If you gauge fix the z's in any particular way, then in order to see all the poles, you have to do some analysis of how the integral is diverging as you go to the various corners in your gauge fixing. And some of the poles will look straightforward, and some of them will need you to be careful about how the z's scale as you go to the corners. And sort of technically, you're doing a blow up on the space in order to see what is going on. Okay, so and that's what you have to do. If you literally take these formulas and gauge fix and look at the integrals, it's not trivial to see where all the poles are. And that's what these U's are doing. You see, the claim is that the product over ij of zij to the alpha prime pi dot pj. So this is a cool fact, is the product over all ij of uij to the alpha prime xij, where these x's are now the honest things that show up in the poles. Okay, where the uij are related to the zij as this cross ratio that I mentioned before.
This kind of looks like this Mellin trick, right? I mean, this semantic trick. I don't know. This seems to familiar from conformity theory manipulation.
I don't know. I'll think about that. Yeah, I'm not. Yeah, but in any case, you see what's so this is not a trivial fact. I mean, it's a simple linear transformation, but it's cool that you can repackage the combinatorial. See, this is what comes out of the correlation function of vertex operators directly, right? That's what you get from the correlation function of vertex operators directly. But this repackaging is what makes it sort of manifest that these are the poles. And especially because these U's are exactly the guys that satisfy the U plus U equals 1 equations, okay? And which then have this beautiful factorization on their boundaries and so on. Okay, so those are the sort of two ingredients that are going in here. One of them is just the positive parameterization, and the other, the other one is that the U's are packaging the information in this way that makes the boundary structure and so the singularity structure as manifest as possible. And something else that they make completely manifest is why the field theory limit works. Okay, so this is another way of seeing that there's all these things. So remember, I gave you this expression for the U's back in terms of these Y's a moment ago. Okay, and so you can ask, well, I'm doing this integral over Y space where Y's are going from 0 to infinity. Let me write all the Y's as e to the t so that the t's go from -infinity to infinity. And then what you can easily see is that while the U's are sort of complicated, slightly complicated polynomials, ratios of polynomials of the Y's, that this t space gets broken up into cones in such a way that asymptotically far in each cone, the U's become effectively dominated by single monomials. And for example, out here asymptotically in this bottom quadrant, the U13 turns into e to the t1, U14 turns into e to the t2. These are both going to 0. That means that all the others are going to 1. Okay, and so that means that this quadrant, this little cone in t1, t2 space, way down here, this integral of u to the alpha prime x just becomes Schwinger parameterization. It just turns into the Schwinger parameterization of this diagram, right? So that's how you can think about these U's. These U's are sort of nonlinear variables that are not associated with any one Feynman. They don't know anything about diagrams. They're just something to know about the combinatorics of the surface. Sorry, the combinatorics of crossing crossing and non-crossing chords. But in extreme regions of the space of integration, some of the U's go to 0, all the other ones go to 1, and in those regions, you can think of the U's as the logarithm of Schwinger parameters. Okay, and you can think of this U integral as nothing other than the Schwinger parameterization of the corresponding propagates. So that if we look at this example, as we go out in every direction, only two of the u's become small, the rest go to 1, and the integral in each direction becomes precisely the Schwinger parameterization of the corresponding diagram. But all the diagrams are unified in one object. And of course, as alpha prime goes to 0, we get we get back the sort of canonical form associated with the surfacehedron, or the in this case just the associahedron. Okay, so we see that the sort of binary realization of the compatibility, which is linearly captured, but this binary nonlinear representation of the compatibility, which is linearly captured by the surfacehedron, has the interpretation of turning particles into strings. Now that was the story at tree level. And again,
I have a question. Could you indicate how the alpha prime goes to zero limit, going to zero limit, actually turns the u's into e to the t's?
Yes, yes. Well, no, the u's, no, that's not, the u's don't turn into e to the t's as alpha prime goes to 0. It's instead that as you go out asymptotically, in each cone, in each cone, as you in each cone, as the variables become large, we get the u's turn into the e to the t's of the corresponding Schwinger parameters for the diagrams. And what's going on is that as alpha prime goes to 0, we should be getting a divergence in the answer, right? That we put this overall factor of alpha prime to the n out in front to account for that. But let's say you remove that. As alpha prime goes to 0, the answer is going to be divergent. Why is it divergent? It's divergent because we have this divergence from the only place that there's divergences is in these extreme regions of integrations as the t's go to infinity. So this shows you that the divergences that you have as alpha prime goes to 0, which correspond to going out to infinity in each one of these cones, can be interpreted as Feynman diagrams. Okay? So that's the sort of and this has nothing to do with the surfacehedron in particular. This is a general thing. We called it a number of years ago stringy canonical forms associated with any polytope. This is a way of sort of getting the canonical form of a polytope that naturally comes along with an alpha prime. But such that as alpha prime goes to 0, it literally reproduces the canonical form of the polytope, and it's for this sort of it's for this sort of this basic reason. So it's not that the u's turn into e to the t, and in fact that's kind of the interesting thing is that the u's they look like different e to the t's depending on where you are in this space. So they jump as you cross these sort of walls. They jump from one form to another. So they morph into the different diagrams in different regions in T space, but they're all just a single object. All right. So what we've been discovering over the past number of months is the extension again of all these things for all surfaces. Again, remarkably, it turns out that it begins just with a story. Again, no metric, no hyperbolic geometry, no nothing, just pure topology, pure sort of combinatorics of crossing chords on surfaces. And you write down the following equation. So for every chord x in any surface, you write down ux plus the product over all the other chords of uy to a power, where the power is simply the number of times the chord x intersects the chord y, is equal to 1. So in the case of the disk, those intersections are either 0 or 1. In more general surfaces, we can have general intersection numbers. But the claim is that this is a set of binary equations that remarkably has a correct dimensional space of solutions. And you can think of this as giving a global set of coordinates. These u coordinates are a global set of coordinates that describes the compactification of the full Teichmüller space associated with a surface. This is very closely connected to, but again, it's a repackaging of a famous local description of the compactification of Teichmüller space given by Fock and Goncharov in the mid-2000s, eventually made contact with the story of cluster algebras and all sorts of other things after that. But these U variables are new. This binary property of the U variables is new. The fact that we have these, that we can just write these equations down without any reference to any auxiliary structure, and then go about discovering different auxiliary structures as ways of solving them is something that we're thinking about more. So again, there are concrete solutions of U equations are either associated with hyperbolic geometry or other pictures that I don't have any time to talk about, but this is where the connection to quiver categories and representation theory comes in, where they have totally different conceptual sort of ingredients that go into it. They look absolutely nothing like a picture of a world sheet or points moving around. It's just something much more abstract. But amazingly, they give you exactly, they also give you solutions with these U equations. And perhaps we'll find other ways of thinking about them as well. All right, so what I just showed you a moment ago is the story at tree level. And now I'll just tell you what we've been finding. Originally, when we ran into these, how to think about these U equations, we ran into what we thought of as a minimal version of them, where the curves that show up, the curves that you care about on the surface, are non-self-intersecting. And there turns out that there is a set of U equations that are exactly of the type that I discussed, which are satisfied by non-self-intersecting curves. You can then take those guys and now talk about them beyond for general surfaces. For the disk with one puncture, that would be one loop amplitudes. The annulus, that would be double trace one loop amplitudes, and so on. Okay, you could go on for any surface. And because these are essentially Schwinger parameterization, you see all the dependence on the kinematic variables, it's through this sort of general U to the X, that including all the loop variables are just sitting up there exactly the way that they do in Schwinger parameterization. That means that you can perform the loop integrations trivially as we normally do in Schwinger parameterization, and you're really left with just an integral over these Y's to represent the whole amplitude, not just the integrand of the amplitude, but the actual amplitude. And then in this language, if it so happened that the surface had a mapping class group, then you'll end up with an infinity if you don't mod out by the mapping class group after you've done this. So of course you have to mod out by the mapping class group as well, but that's now done post doing the loop integration. So this is really a picture for the actual amplitude as an integral over these Y's modulo the action of the mapping class group when it exists. And over the summer, we started exploring what these integrals look like at one loop. And we noticed that they didn't really look anything like standard string theory integrals at one loop. There is, at one loop in string theory integrals, you're used to seeing elliptic theta functions. You're used to seeing Jacobi theta functions and Euler eta functions and so on. And we didn't see anything like that. We just saw these relatively simple polynomials showing up. But we studied, for example, the high energy behavior of these amplitudes, and we found they're exponentially soft in the physical regime, just like string amplitudes are. So they had clearly some stringy properties, but they really didn't look like they were honest string amplitudes. So we're very puzzled by that. But then purely by thinking about the combinatorics and this quiver representation theory and the basic mathematics, we actually realized that this minimal binary geometry lives inside the maximal version of this story, where you think about all curves on the surface, including ones that self-intersect any number of times. And if you run that story at one loop through the same machine, where we just take this formula, appropriately interpreted, but now including all the curves on the surface, now we start getting much larger infinite products from all the self-intersecting loops. And remarkably, we find precisely things that look like one loop string integrals with all the Jacobi theta functions and all the stuff that we expect to see at one loop. Okay, so this thing that we saw before is some kind of baby string amplitude. Both this baby string amplitude and the real string amplitude, as alpha prime goes to zero limit, reduce to field theory amplitudes. But it's very interesting. We think that there's this sort of way of finding this much coarser story with fewer loops on the surface, And as we increase the number of loops on the surface, we get closer and closer to the real string amplitude. All of these things have including the simplest one, are some kind of ultraviolet regulator of the low energy field theory. They combine all the diagrams into one object. They do everything that they do all these classically stringy things. Very likely what's wrong with this baby string amplitudes is that if we interpret them as physical amplitudes at finite alpha prime, they'll probably fail to be unitary. They'll probably fail some cutting condition at finite alpha prime. They're fine as the regulators of the field theory amplitudes, but probably at finite alpha prime, the guess is that they'll fail to be unitary, and that it's these real string amplitudes that are sort of maximally physically consistent. And of course, you will discover the critical dimension and so on by as Lovelace did in the early days, directly from the one loop amplitude, by demanding that illegal cuts in the annulus amplitude are turned into poles, which only happens in the critical dimension. There are other interesting things. These are completely non-supersymmetric theories, and yet we have ways of computing these amplitudes that involve the emission of tadpoles and the master normalization bubbles, which we can control. I mean, there's nothing in the integrals that tells you that the thing is running away. It appears to be, well, we don't know exactly what the physical interpretation of this entire class of objects is, other than the fact that the maximal version definitely seems very, very closely related to real string amplitudes. But it could be that this whole set of ideas is providing another set of natural coordinates with which to talk about the integral over marginalized space, and to even think about what the string amplitudes look like at loop level and beyond.
Have you checked the alpha prime going to zero limit?
Sorry?
Have you checked the alpha prime going to zero limit for these?
Yes, it's all guaranteed. You see, whether it's baby or real, they're all guaranteed to be correct as alpha prime goes to zero for this general reason that I explained. The only difference is that this is the sort of amusing thing. You see, let me try to explain this point.
Nima, maybe I can ask you a question which you can fold into your answer, if I may ask, or not answer, which is, I mean, let's say we take pure glue QCD in the large N limit, and you construct its baby amplitude, your baby field theory version. Are you saying from that, by considering the maximal version, you can construct a legitimate string amplitude?
I believe so, yes. Well, see, what I really have here is again that
okay.
So what I strictly have, what we strictly have is this trace phi cube theory. Again, there's no known string background that is literally this theory. Okay. However, there is something sort of universal about what we're talking about. We're talking about the correct pole structure for any theory. So what happens when you look at string amplitudes, even at tree level, is that there are these sort of backbones which are worldsheet integrals, and then they get dressed with various things with polarization vectors and kinematics on the outside that tell you whether you're talking about gluons or some massive string state or whatever. But there's a sort of backbone is this integral, the Cohen-Nielsen-like integral that has the correct singularities and the correct kind of factorization built into it. Then there's something important about the sort of numerators of the polarization vectors as well. But that's where the choice of who you're scattering and what theory you're talking about more precisely comes in. So what I think is going on is that we have something which is capturing all of that without any of the numerators yet. Okay, so but it's giving us a way of thinking about a different way of thinking about the worldsheet integrals, and a way of thinking about them where the sort of connection to the degeneration of the surface is just hardwired into these binary equations. So you start with these binary equations, and they have solutions and integrals that look like integrals that are softened by powers of these u's are guaranteed to have the correct field theory limit. Just guaranteed to have the correct field theory limit. But if you add to these integrals also powers of these self-intersecting variables, it looks like, and if we do it in the most natural way, now I haven't told you how we assign momenta to all of these arcs and so on. So that's the, well, since my goal was not to talk for 5 hours, but I'm getting close to that anyway. Maybe I failed in my attempt to just talk about some vignettes. But anyway, there are ways of there are canonical ways of associating exponents with any curve. And if you apply those ways also to the self-intersecting curves, then what you get from these integrals are the theta functions. Okay, what you get from the integrals at one loop are the Jacobi theta functions, exactly what you expect at for string one loop amplitudes. And presumably, if we dress that up with polarization vectors and momenta, just like we would at tree level to turn them into gluons, they would turn into gluon one loop amplitudes if we kept going. That's the part of the story that we still don't know. What's the story of the numerators, roughly speaking? We figured out the story of the poles and the stringification of all the poles. We don't yet know what the stories of the numerators. And presumably, this is also related to the check that we have not done. It's a very difficult check to do, even in ordinary string theory. I don't think it's ever been done, even in ordinary string theory, is literally check that at finite alpha prime, the amplitudes are unitary. And presumably, at some point, these dumb scalar models will fail that. They don't fail it at tree level, by the way. They could have failed at tree level. It's non-trivial that even on the massive poles, these amplitudes are unitary in the critical dimension, in less than or equal to 10 dimensions. So, but I'm guessing that there is no actual consistent theory here, just with this dumb phi cube structure. And at some point, there'll be something that breaks down. Probably something will break down in a unitarity check, in a cut check at one loop. And that's where presumably you have to start putting in the correct enumerator structure, the correct yeah. But that's all if you're trying to make something.
String theory is not unitary.
Sorry?
Are you saying that ordinary string theory is not unitary?
No, I'm not saying ordinary string theory is not unitary. I'm saying that explicitly checking unitarity at one loop is very difficult. That no one has taken a 4-point expression and literally checked the cut at finite alpha prime. No one even knows what kind of function you get at finite alpha prime. Never mind. Now there is this double dispersive representation of Docker and Fong for 4 points, which is probably pretty close to explicitly checking unitarity. But it's a lot of work to get, and I can't remember if there's been an explicit check of unitarity. I mean, an explicit check of unitarity even at tree level is very non-trivial, because explicit check of unitarity is showing that the residue on the massive poles can be expanded as a positive sum over Legendre polynomial, and that's extremely non-trivial. The only proof, again, is very indirect through the no-goats theorem. But I'm saying if you didn't know anything about if someone just handed you the answer and you wanted to check that it's unitary, even at tree level, it's very non-trivial. As far as I know, there is no. Well, we have some work coming out where at least proves it up to 6 spacetime dimensions. Up to 10, we still don't know how to do it directly. I mean, directly from the from just looking at the answer, even at the tree level. But I suspect that's where the problem. That's if there's a problem, that's where the problem is. But both the baby string theory and the full string theory, they're soft, exponentially soft. And they all give you the correct alpha prime goes to 0 limit. So there is some object out there which does the same thing string theory does, as far as combine all amplitudes together, that level, all the same things, not string theory. Much simpler, vastly simpler. And the path from that object to the full string theory is something looks very natural. Looks like going from the minimal version to just, it looks like adding self-intersecting curves is like adding the effect of making it more stringy. Oh, sorry, I forgot to add this picture. I wanted to explain why the self-intersecting curves aren't changing the story of the alpha prime goes to 0 limit. You see, when a curve is self-intersecting like this, when you write its U equation, that U plus, because it's self-intersecting, U occurs also in the second term, right? So even to some power. So this means that you cannot go to 0. Okay. So if you have a self-intersecting curve, it is never relevant to the boundaries. Okay. So if we have these, if we have self-intersecting curves, they can never go to 0. They can never be associated with any massless poles. So you can add them, you can not add them. It makes no difference if the alpha prime goes to 0 limit. However, they do seem to be important to, well, they're definitely naturally there in the full mathematical structure. They're naturally there. They really, you do not want to ignore them. And when you include them and you look at those infinite products, you do quite beautifully get the kind of the elliptic functions that we expect to get for annuli and tori.
But you're motivating your field theory limit. You're motivating your field
Excuse me. Sorry. Let me just suggest that we postpone the questions to the end of the talk. Let Nima finish now because it's already been quite late. So, if you don't mind, let's postpone the questions.
All right. So let me maybe just give you some idea of how we can understand these infinitely many U equations. Let me show you what it looks like for the annulus. Okay, so here's an annulus, and I've drawn a bunch of curves here in different colors. So here's a self-intersecting curve in purple. In green is like a normal curve that winds around a couple of times. Okay, but it doesn't intersect itself. And here's a red curve. It just goes from 1 to 2. Well, you know that you can take any Riemann surface and uniformize it. So I can think of it as the upper half plane modulo a certain Fuchsian group. And in this case, we don't have to say anything fancy about Fuchsian groups. It's very intuitive. How do I make an annulus? Well, imagine here I have a point like Z1 corresponding to this guy up here. And I'm just going to rescale it by some lambda Z1, lambda squared Z1, and lambda inverse Z1, and so on. So I'm going to rescale it infinitely on the left and take the point Z2 here and rescale it infinitely on the right. And now you can see that if I look at any sort of quadrilateral here, like I didn't draw it, but if I draw a sort of a quadrilateral from Z2 to Z1 and lambda Z1 to lambda Z2, that's like a fundamental domain. And then I'm just copying that infinitely often, the same way that you would draw for to make a flat cylinder or a flat annulus. You just draw a bunch of strips with identification. I'm just taking those strips and embedding them in the upper half plane with identification. Okay, but so that's the hyperbolic picture of the annulus. But now you see, I can think of this as as like a tree level process, just a disk with infinitely many points. So I have an infinity gone, where on the right I have these points of the form lambda to the j z1. On the left I have these points of the form lambda to the little j times negative z2. And the identification that gives me the annulus is just would just take any pair of points here, or take any UAB, whether AB is on the left, where the A's are either the little I or the capital I indices on the left or the right, and I can translate them both by 1. Okay, so in other words, I begin with an infinite gone, but with these interesting identifications. These identifications here, I motivated it by drawing a picture of the hyperbolic plane. But again, I don't have to say anything about hyperbolic geometry. I can just work with these U's and say that there's an action of the homotopy group of the surface on these U's, which in this case, the homotopy group is just Z, and the action is just trivially shifting these indices by 1. The remarkable thing is that the binary equations for the disk, once I make these identifications, you see, in other words, I'm just going to write down U plus the product of all these crossing U's is equal to 1. But the product of all the crossing U's, there's a bunch of identifications inherited by what I just mentioned above, and so the exponents end up precisely giving you the intersection numbers. Okay, so that's at least a picture for how we can get these U equations for a general surface by uniformization from what we know to be true for the disk. Okay. All right, I don't have any time to talk about this, but maybe I'll just say super quickly, the connection to quivers and quiver representations begins again by taking your surface here. I've just drawn the 5-point tree, so just the disc with 5 points on the outside, and I triangulated it. And there's a sort of a standard way of, from a triangulation of a surface, getting a quiver. What you do is inside every triangle of the triangulation, you put a dot on the lines of the triangulation, on the chords of the triangulation, and then you connect them up with triangles again in the following way. So if you do this in this case, and you only look at you only keep the dots on the internal chords of the triangulation, starting from this 5-point problem triangulated in this way, you get the following quiver. And it turns out there's a whole story for what you should do now is think about this quiver as giving you just general maps between vector spaces. So you imagine that you attach to every node of the quiver a random vector space, and the maps are general maps between pairs of vector spaces. And then you're really trying to understand all the possible representations of this set of maps between vector spaces. So there's a notion of an irreducible, or they call it indecomposable representation. And then there's a whole world that begins from there to look at all the indecomposable representations of associated with a given quiver. Then you look at another object, which is a different category, a category where the objects are a representation of the quiver, and there are maps between them if there's morphisms between the two representations. That path to go from so you go from the quiver, you think about representations of the quiver, and then you think about a new category that has the representations as objects and arrows between them as being morphisms between the representations. That leads to something in this theory that's known as the Auslander-Ruyten quiver. And this Auslander-Ruyten quiver is going all the way back, is the origin of our kinematic space-time. These pictures that we sort of intuitively draw in this, drew already in our simplest case, they actually have a deeper meaning. All of these nodes are actually associated with certain representations, and there are arrows here that are not drawn that are actually morphisms between the corresponding representations. And when you run through this story, it turns out that with every representation, there's a certain simple polynomial associated with them. There's certain simple function u of r, which is simple monomials and what are known as the F polynomials associated with the representations R, and that the U equations have this sort of a beautiful generalization where the powers of the UI have a natural interpretation, not directly just in terms of intersection of curves on surfaces, but of counting dimensions of maps between different the dimensions of map of vector spaces of morphisms between representations. So what this does is, in the case of surfaces, it maps to the story that we talked about, but actually gives us a generalization of correctly factorizing particle and string amplitudes, which are associated with much more general quivers that don't have any obvious connection to the normal world sheet. And it's these, I should say, it's these ideas that Alok Lada and friends have been exploring in finding the analogs of these kinematic of these associahedra for phi to the 4 theory and phi to the p theory. So all of those things have these binary realizations, and I think it would be very interesting to try and understand how they work. All right, so maybe we can end. So I just want to summarize that over the past decade, we've been seeing some concrete examples where the rules of locality and unitarity emerge from more elementary mathematical rubric. There is a common theme in the story of amplituhedra that I didn't talk about at all today, the surfacehedra that we just talked about, are notions of positivity and topology in kinematic space. And it's these really simple notions. Again, if we think about the last part, the middle part of the talk we just had these the simple sort of the wave equation in kinematic space, where it was important that we had positivity and we had positivity both of the x's and of the sources. In the third part of the binary geometry, it's just literally just topology of the surface, nothing else. You write down these binary equations and ask for everything is positive, and poof, what you get is an object that factorizes on its boundaries, and these simple integrals associated with them seem to have the richness, and they all give you the field theory amplitudes as a single object at low energies, and they might even connect in general to string amplitudes. So it's both positivity and topology that play a central role here, and that's what we've earlier seen plays a central role in the story of the amplituhedron as well. Now we're still looking for general principles. One thing I should say is that there are clues that amplituhedra and surfacehedra are connected to each other, and you can think of the surfacehedra as being something that captures the kind of very universal singularities associated with factorization that are there in any theory. And the surfacehedron itself is flat, as I described it. It's a polytope of flat facets. Now the amplituhedron is something that's there in n equals 4 super Yang-Mills, but again, the singularities that are captured with the amplituhedra are universal for any Yang-Mills theory in the planar limit. And the important thing is that it captures also soft limits, not just the factorization, but also soft limits. And while it might seem trivial, it's not. And the fact is that the soft limits and the factorizations are all sort of unified into this larger structure that correctly captures all of the singularities of planar Yang-Mills-like theories. So in this way of talking, it's clear that the surfacehedra should, at least for the planar diagram, should somehow sit inside the amplituhedron. And indeed, people have seen already direct connections between the associahedron, in some sense, living inside the amplituhedron. I should stress that the amplituhedron is a curvy object. It is not flat. It's a curvy object. It's a very nonlinear object. It's a vastly richer and more interesting object than the surfacehedra. So the fact that this is sitting inside it is very natural, and it'd be nice to understand the connection more. On the other hand, we have this other curvy version of the surfacehedra. Now, this is literally a curvy version of it, and that's these binary surfacehedra that are connected with strings. And over the past year, there's a few examples emerging of some connection between these binary geometries on this side, and at least the simplest amplituhedra on this side, due to work of some mathematicians and physicists. So it's conceivable that there are more connections between these objects yet to be discovered. All right, I think I'll stop with that. Thanks a lot.
Okay, thank you very much, Nima, for a wonderful and clear talk. Let's all unmute and applaud. So we have had it has been a long seminar, so we should only have a couple of urgent questions. So I see Debashish Goshal's hand up, and also Somdatta was asking questions. So maybe Somdatta, you can ask, and then Debashish, you go ahead, and then we start.
Yeah. So this surfacehedra is a more general thing, right? Because it involves the string theory, and the string theory is kind of encompasses the field theory and something else. So I don't understand how the surfacehedra can be a subset of the amplituhedra.
No, the surfacehedron is the surfacehedron polytope. The surfacehedron polytope has nothing to do with alpha prime. The surfacehedron polytope is just something that just captures that captures as a flat polytope. It captures all the combinatorics of pinching the curves on surfaces, and all of those singularities are at least, if we only were talking about planar diagrams, all those singularities are a subset of the singularities that are captured by the amplituhedron. there's a very good reason why the sort of the singularities that are captured by the surfacehedra that at least correspond to planar diagrams should be a subset of the ones captured by the amplitude. So that's
but the amplitude hedra and the surface hedra are not, they are not just concerned with the singularities, right? I mean, they are associated with more.
That's the kind of fascinating thing, is that again, if I had a little bit longer, yeah. So let me say it like this. This is the zeroth order. I mean, this is one of the zeroth order things that has been discovered in this business, is that once you've found some sort of geometric shape that correctly captures all the singularities and how they meet, you know, the sort of combinatorics of how they meet. These are very non-trivial shapes. That's the zeroth order surprise, is that you think, oh, there's some dumb counting problem, but there's some very non-trivial shapes that capture this. And then for some special theories, knowing the shape completely determines the amplitude. That's the kind of amazing thing. That's this connection between the shapes and the forms of logarithmic singularities. So for example, in the case of the amplituhedron, there is this way of capturing all of the possible singularities at tree and loop level, at least for planar n equals 4 super Yang-Mills, purely in terms of some very simple generalization of polytopes into the Grassmannian. So that's what the amplituhedron is. It's a natural generalization of the notion of polytopes into the Grassmannian, and if you look at all of its boundaries are just capture every possible singularity, including the most degenerate, crazy ones that we normally don't think about, with many things going soft and collinear at the same time, of Yang-Mills at loop level, even ordinary Yang-Mills, even like pure glue. Okay, what's extra about n equals 4 is that the actual amplitude is completely determined by that. And it's completely determined by being a form that has logarithmic singularities on the boundaries of that space. More general theories can have singularities elsewhere. For example, Yang-Mills theory will also have singularities on some locus at infinity. That's associated with the beta function of the RG and all the rest of that stuff. Okay, so there's also some singularities elsewhere associated with the ultraviolet. But there's a bunch of universal singularities that are the long distance singularities, and they're in common between all these theories, supersymmetric or not, just they have to be planar. But n equals 4, once you know them, this form of logarithmic singularities captures the whole thing. So similarly for these surfacehedra, the singularities we're talking about are universal for any theory. Different theories will now have numerators that we're not talking about here. But if we just talk about trace phi cubed, once you know these singularities, you're done. The form of logarithmic singularities on the space is the answer. So that's so right. You might have thought, oh, there's much more going on than just the singularities, but there's not as much more going on as you would think. And so the perhaps ultimate hope is that we'll find some extra lessons about what's supposed to capture these singularities at infinity, and that adding the knowledge of what's going on with the singularities at infinity together with what captures all these long distance singularities will give us a sort of complete set of rules for much more general theories.
Another thing
but that's why just at the level of geometry, nothing else, the sort of factorization singularities are a subset of all the singularities in Yang-Mills, and therefore the kind of polytopal geometry, the combinatorics and the polytopal geometry of ordinary surfacehedra should be a subset of those of the amplituhedron. By the way, there are many other indications that the amplituhedron is much richer than the string worldsheet. At the most primitive level, at the tree level, it's just a generalization of you can think of the tree level string worldsheet as the m equals 2 version of the amplituhedron that makes sense for any m. One way of thinking about it is some generalization of the worldsheet to where instead of having SL2, you have an action of SLM in general. So that's part of the connection that's starting to be developed more now as well.
So why is the surfacehedra determined by the singularities? I thought string theories don't have any singularities.
The surfacehedron has nothing to do with string theory. Zero. Okay.
So
I mean, strictly, of course, they're all related, but I can in principle talk about it without ever saying the word alpha prime. That's why there was that's why they were in separate parts of the talk. The surfacehedron is just capturing it's something purely topological. That if you take a surface and you draw curves and you just imagine cutting the surface along the curve, the surface does something. It splits in two, or it turns into another surface in some simple way, and the claim is that there is an object that you can decorate the facets of this object with these ways of cutting surfaces. It has nothing to do with any alpha prime. There's no alpha prime in the story at all. It's some sort of purely combinatorial fact about the compatibility of curves. It's a topological fact about the compatibility of curves on surfaces. Yeah. So what does have to do with an alpha prime, and or at least more closely related to the alpha prime, is this remarkable fact that that compatibility has this binary realization. This is definitely not true for random polytopes. If you take a random polytope and say, okay, in this polytope, these faces don't meet, these faces don't meet, these faces don't meet. So can I write down some nonlinear sort of binary equations that gives a binary realization of that? Absolutely not. So it's a very magical thing for a very special sort of class of polytopes for which this is true. However, it's true of the polytopes that are associated to surfaces. It's also true for this more general set of objects that go beyond surfaces. So that which I didn't really have any time to explain what they really mean, but that's this association with quiver representations. There is a much larger set of objects of which surfaces are just a very special case for which this kind of magic happens.
So surfacehedra related.
Sorry, let give Debashish a chance. So Debashish, go ahead, please.
Yeah, sorry. First of all, thank you for a very fascinating talk. I have a very brief question that's to do with the number of space-time dimension. Does that play any role? Because the way you described it, it seems to be true for any dimension.
Yeah, that's right. In this talk, none. And in fact, it was important that, I said that these Xij's are a basis of Mandelstam invariance, for example, at 4 points, at tree level. And they're really a basis of Mandelstam invariance in principle in infinite number of dimensions, because in any finite number of dimensions, as n gets large enough, there are relationships between the Mandelstam invariants, right? There are these grand determinant conditions that tell you that you can't have more than n independent momenta in n dimensions, right? So we have those. So those are nonlinear conditions between these x's, and I'm ignoring all of those. So that's right. So in this talk, there is no. It could be in principle in any number of dimensions. Now you could ask, where would I discover something like the critical dimension? And there it would come from more physical considerations. All these objects that I defined, their main purpose in life is that they have poles in the correct places and they factorize correctly. And when I was just talking about sort of field theory amplitudes, that's all there is. In these binary integrals, that is true even at finite alpha prime. So that's not non-trivial. Even at finite alpha prime, the ordinary, but the massless poles, they have factorized properly. However, if for it to be physically meaningful, we also want them to factorize properly on the massive poles. Already at tree level, already at 4 points. If you take the gamma gamma over gamma formula, then it has all these massive poles. And if you sit on a massive pole, you want to check that it's in fact that it can factorize into the product of 3-point amplitudes. But that requires that the residue on that pole should be expandable in a partial wave expansion, should be expandable as a sum over Legendre polynomials with positive coefficients. And that's a very difficult thing to check explicitly. It's you know, so there's a very and it turns out to only be the case in less than or equal to 10 spacetime dimensions. Okay, so you can already check if you've never seen this exercise. It's an amazing thing to do. Already you see in the simplest case on the third massive pole, you just discover that the residue would have a minus sign in it if the number of spatial dimensions was if the number of space-time dimensions was 11 or higher. So there's already the kind of physics of the critical dimension is sitting there in an extra check, which has to do with unitarity on the massive states. Whereas the entire story I talked about was focused on the unitarity of the massless states to begin with, because that's the only thing I was talking about. And then even in the stringy version, it was unitarity on the massless poles, although at finite alpha prime, right? So somehow that there seems to be an extra set of constraints coming from full unitarity, including the massive poles. And of course, what would be wonderful is if that story had a similar, you know, you see, the thing that I like about this this subject is that we're not constantly checking locality and unitarity, you know, we sort of make a guess for these different structures, and they and which then give these checks a new interpretation, right? They give these checks a new origin. They're not checks; they're things that just come out of these new kind of questions. So it'd be wonderful if the checks that give us d equals 10 and maybe check unitarity beyond on the massive states at non-zero alpha prime come from some appropriate extension or deeper way of thinking about the structure. That I don't know yet.
Thank you.
So Nima, if you don't mind, we can take one more question.
Sure.
Okay. So Abhijit, go ahead.
Yeah. Hello. Yeah. So I was just wondering if for the one loop level, if we go from the integrand to the loop and amplitude, we have to integrate, right?
Yes.
One more thing. So in the integrand level, we are having a nice geometric picture that it is a type D cluster polytope. But at the amplitude level, what is the picture for the loop level story?
Yeah. Well, I mean, it is. The point is that you can do the loop integral very easily because the dependence on the loop integral because all the loops are just occurring in these exponents, so it looks just like Schwinger parameterization, right? So you can think of it like this. Are you familiar with the how we normally think about loop integrals? Even for a single Feynman diagram, right? We have a single Feynman diagram, we Schwinger parameterize, and then you're left with this integral over these U and F polynomials, right? They're these semantic polynomials, right? We have these, and in fact, the semantic polynomials have a very nice geometric interpretation of their own. So there are these polynomials, the U and the F polynomials, and the Newton polytopes of U and F have very beautiful properties, and they also have factorization properties. They have all kinds of geometry associated with them. That's a whole other subject that something that we'll hopefully have a paper about soon. But anyway, there's some so now what's going on is that when we do loop integrals, because these U's are like a universal Schwinger parameterization, what we're getting is an integral over what would look like the semantic polynomials of a complete graph, where all the propagators are there, everything is there, and then so you have an integral where the integrand looks exactly like the act of doing the loop integration gives you exactly the semantic U and F polynomials, but they're parametrized by these U's. So it's so we don't know what the full geometric interpretation is yet, but it's some very interesting admixture between the sort of semantic polytopes and these binary surfacehedron things. So there's some kind of jam between the two of them. The only general thing that I can say is that one of the very zeroth order features as where are the ultraviolet divergences, where are the infrared divergences. And you can very easily see, for example, at one loop, that the only place where the loop variables come in would involve these the U variables for variables that would correspond. You know, if I draw a picture like this at one loop, let's say at 4 points. Can you see my screen?
Yes, yes.
Okay, so I'd have these guys. I'd have these, you know, some y1, y2, y3, y4. Then I have the other kinds of chords too. So, but clearly I have uy1 to the L squared. So the overall dependence on loop momentum for a large L just goes like uy1 through uy4 to the power of L squared, right? So I'd have something like this. So that means that so when I do the loop integral, I'm going to get a 1 over log of uy1 through uy4 to the power of d halves, just from the Gaussian integral. When I do the integral over L, if I do something like d4L, I'll get something like this. So that says that the singularity comes when these U's. So the ultraviolet divergence, the ultraviolet region, is when all these uy1 through uyn are all going to 1. Okay, so that's the interesting UV region. And what's fascinating is that you can actually see directly that is this is how the usual fact in string theory that ultraviolet poles, ultraviolet singularities get turned into infrared sort of closed string poles arises here. Again, purely primitively, first as a statement about what this binary geometry looks like, because you can just see that in the limit that these U's all go to 1 is really like a limit where you have a little hole in the surface, and this and that size is shrinking to a 0. So as this thing goes to 1, this hole is shrinking to a 0 size, and it just becomes exactly as if you have a puncture here. And then purely at the level of the U equations, you can see that these are the U equations that you would get just for this punctured surface. And so this exactly has the interpretation as a closed string emission. So that's an example of part of this geometry, is that when you do you don't see this before you do the loop integration. Before you do the loop integration, there's nothing happening when these U's go to 1. After you do the loop integration, there's this sort of ultraviolet region that corresponds to the U's going to 1. And you can see that what that region looks like in the binary geometry, it's not one of the boundaries. It's kind of in the middle of the space. But in that middle of the space, in that locus where the integral develops a singularity, it looks exactly like a different problem with the addition of a closed string.
Thank you very much.
Okay, thank you, Nima, again for a wonderful talk.
All right, thanks a lot, guys.
Thanks a lot. Let's all applaud again.
Thanks. So long, guys.
Thanks so much. Bye-bye.
Bye, guys.